There we go.
Okay, thank you. So just to make sure that the online audience got what I was talking about, all I was saying is this is a very basic introduction to MPI, and I will share information about running MPI programs on Stampede. And I assume that you already have understanding of C or Fortran programming, and you have access to either Stampede or a local installation of MPI in order to take part in the hands-on session. So let's quickly go to the basic concepts related to MPI. So just as a heads up, MPI is just a specification for message passing library that is standardized by MPI Forum. By itself, it is not an implementation. It just lays out the guidelines of what an MPI implementation should look like. So there are multiple vendor-specific implementations of MPI, and some of them are like MPI-CH or MPitch, MWebPitch, Intel MPI, OpenMPI. And on Stampede, we have both Intel MPI and MWebPitch 2 available for you to use. And note that the programming model associated with MPI is distributed memory. However, you are able to run run MPI programs on shared memory or distributed shared memory machines as well. And the whole point of message passing or MPI here is to let processes which are running in independent address spaces to communicate with each other. Now you might think like, why do processes want to communicate with each other? Well, they need to communicate in order to exchange data, in order to synchronize, and so forth. So when you write a distributed memory model program, then basically you're dividing a big task into small pieces, or you're distributing a big data into small pieces, and you're engaging multiple processes in parallel to do the computation. And each process runs in its own address space. So unlike shared memory programming that you went over yesterday with Victor, unlike that model wherein they have a shared address space, in MPI world, even though the programs might be running on shared memory machine or distributed shared memory machine, each process has its own address space to work with. Okay, so in order to exchange the data, in order to synchronize with each other, they need to send messages to communicate with each other, and that's where MPI comes into picture. And MPI specifications have been defined for C and Fortran languages, and they are credited for portability and performance. And the recent most version of MPI standard is we are at MPI 3, and the latest version that was released earlier this year is MPI 3.1. So this diagram that you have on slide number 6 is just to illustrate the high-level view of how a big program can be broken down into smaller pieces and run on different nodes or different cores of a node independently. So if you look at this diagram, you would notice that each node that I'm showing here in pink color, each node memory associated with itself. So this is the point I was trying to drive home earlier, that it's a distributed address space, distributed memory that we're talking about here. And notice that I have a block of data in blue, let's say here, and what I'm trying to do is chunk it into 4 pieces, and I have 4 nodes over which I would be running this program, let's say, individually. And then each node gets a block to work on. And notice that there is this interconnect that's connecting all the nodes. This is just a very coarse grain level picture. And you notice that this MPI layer, it sits on top of the interconnect. So that's how you can visualize that. It gives you a fabric of communication. It gives you a topology to orchestrate the exchange of messages between different processes. So that's what MPI does. So I would take a minute here and emphasize that MPI falls under the category of explicit mode of parallelization. So there are essentially two modes of parallel programming: implicit parallel programming and explicit parallel programming. When you do implicit parallel programming, you would use languages like, for example, Extend from IBM or Fortran, right? So those languages already have constructs in them that could be used to implement a parallel program, and all the parallelism is inherent in those constructs that you would use. On the contrary, things like OpenMP or MPI, they fall under the category of explicit parallelization, because basically these are like group of functions or API or pragmas or directives or library calls that you insert inside a C program or a Fortran program or a C++ program to make your program work. So you have to explicitly take steps to do the data distribution in your program, orchestrate the exchange of messages across different MPI processes, do the task of data collection. So it's you as a programmer who have to choose the right function, the right directives if you're using OpenMP in order to implement parallelism. And you might want to look at it as language extensions or libraries that support the existing base language. So the base language by themselves do not have these features ingrained in them. That's why this is explicit mode of parallelization. Okay, so just to give you an overview of how one would typically want to write a parallel program, rather I should say this is how I would want to approach writing an MPI parallel program. I would take a working sequential application. Okay, it could be written in C, Fortran, C++. I say just these because MPI bindings are today available for only Fortran and C. The C++ bindings have been deprecated. So if you're writing a program in C++, you might get by using the C bindings, right? So let's say I have a working C or a Fortran program, for example. Then I would profile the code. I would identify the hotspots or regions of concurrency or where parallelism might lie. And once I identify concurrency in my sequential application, I would want to go ahead and choose a data distribution scheme or a task distribution scheme. And depending upon how I want to distribute my data or task or how I want to do load balancing, I might choose, if I'm talking about MPI, I'll choose the right MPI API to insert in the program. And be forewarned that just picking the right MPI and putting it in the program might not give you a parallel program that works. You might have to restructure your program to expose the parallelism further if it's not very apparent. So we will look at that when we do hands-on exercises, as in what I really mean by inserting MPI API and restructuring your program. But I would just apprise you that there might be, depending upon the size of the program and the amount of parallelism you want to achieve, there might be some restructuring of code that might be involved in the process of writing an MPI program. Okay, that's why I have this re-engineering box here in front of insert MPI APIs, right? So just inserting MPI API will not help you develop a parallel program for most of the applications. And then, voila, you got a parallel program. Now, what you want to do is you want to make sure that it performs well, right? So you performs well, you are able to take advantage of the underlying architecture. So what you could do is some level of optimization. There is some level of compiler-based optimization that you could use, and there is some more manual optimization that you might want to have to do in the code. And this, again, might require some level of re-engineering in your application, okay? So that's the traditional process, or rather, that's how I try to set up my parallelization process, like start with the working sequential application and work incrementally. Okay, having said that, let me show you a general structure of what the whole environment might look like when an MPI program is running, let's say on two processes. So we have process 0 and process 1. Let's say we have just two processes, and I'm running a parallel program. Yes. Oh. Thank you. Top right. This one. Thank you. Thank you. So let's assume that we have two processes, like MPI processes, and I assume you know the notion of a process, right? You can imagine that you have a program that's running on two cores, right? And let's call the program myprogram.c. So the same copy of the program running on two processes. So typically, MPI programs are structured that you would have an MPI include file. So every MPI program ought to have an MPI include file. And then you have a bunch of declarations or prototypes, and the program begins, let's say, and there might be some region of serial code. And after that, there might be something that I'll tell you about soon, which is called, which could be used for initializing MPI environment. So you have to initialize your MPI environment, and then you have to remember to terminate the MPI environment. And everything that you want to do in parallel, that you put inside this initialization and termination blocks that you see here. Okay, so it's from the beginning of this section, as in where we have initialized MPI environment, that's where the parallel code begins. And it's unlike OpenMP. In OpenMP, you are forking. When you come to a parallel region, you fork different processes, right? Here, note that the program is already running on different processes. All this is doing is giving you a context to communicate with other processes, MPI processes in parallel. So that's what I mean by parallel code begins here. And then you do your work in parallel, and you remember to terminate the MPI environment. That's where once you terminate the MPI environment, the processes will not have context to communicate with each other, and then they will start executing, let's say, the serial portion of the program, and the program ends, right? So this just gives you an overview or high-level view of how a general structure of MPI program looks like. Oh, okay. Okay. So now let me briefly mention some basic concepts. So one, there are two places where I will talk about basic concepts, one over this slide and one in the next section. So early on, let me just mention to you that MPI has a notion of communicators and groups. Now, these communicators and groups are objects that are used to define which collection of processes may communicate with each other, right? So all the processes that you have, that you are engaging in your MPI computation, they need to belong to some group, and they need to have a context. And the group and the context together are called as communicator. Okay, so believe me here when I say that MPI gives you a default communicator, which is called MPI CommWorld, and this is the one that we would be using in some of the examples that you would shortly see. So that's a predefined communicator, MPI CommWorld, and that includes all the MPI processes that are participating in the computation. Now, MPI does give you the privilege to define multiple communicators and multiple groups, but we are not going to cover any of that today. We're assuming that all the processes that you have invoked to run your program fall under one group, and they have one communicator associated with them so that they can communicate with each other, right? Just like in a class, you would have a homework project, and it's a team project. So all the students in the class are supposed to work on the project as a team. You wouldn't go to another class and engage other students to work on that program, right? If it's a class project, it's the class as a team who's working. That's the same concept here. So we have this, that's why we have this notion of communicators and groups, so that we have a well-defined context in which the MPI program is running, right? So most of the MPI routines that I will be telling you about, they would need communicator as an argument. That's why it was very important for me to tell you about communicators and groups at this point. So let's go here. It seems like the mouse isn't working. Maybe I'm not using it in the right way. It's just the arrow key that works. Is that right? Okay, okay. So let me quickly go to the section on environment management MPI routines. So as I was telling you when I was explaining you the high-level structure of an MPI program, every MPI program includes an MPI header file. So if you're writing a C program, you have to remember, or C++, you have to remember to include mpi.h file. And if you're writing a Fortran program, then you might need mpi.f.h. And the syntax for, let's say, C and Fortran are shown on the slide. So that's how you would include the mpi.h for C and mpi.f.h for Fortran. And note that every MPI program has a routine to initialize the MPI environment. And that routine is called MPI_init. Now, there are two versions of MPI init that you could be using, and I'll talk more about that soon. But for now, just know that there are routines to initialize the MPI environment, and they are called MPI_init. And every MPI program needs a way to terminate the MPI environment, and that's what MPI finalize helps you to do. If you notice at this table that's there on the slide, I have mentioned two MPI I've mentioned two MPI init like prototypes of two prototypes for MPI init call. One accepts only null arguments, like both arguments are null, and the other one accepts &argc and &argv. So if you are a C programmer, do you recognize argc and argv? So if you write a command line program, you pass argc and argv, you use that particular signature of main function, right? So just in case you have a C program wherein you're passing command line arguments, and that program has argc argv as the part of the signature of the main function, then you could pass that on to the MPI initialization environment. Now, starting from MPI 2 standard, the MPI implementations were instructed to figure the MPI environment automatically. So you had the privilege now to pass null values. So this is passing null to MPI init is as valid as passing argc and argv. So that's about like the MPI init in the C side. Now for the Fortran, it's MPI init, all caps. You could use this notation, or you could use MPI init all in lowercase. So you might want to pay attention to how APIs are, or maybe the function call, MPI function calls are written in C and Fortran. So in C, MPI_x, up till here, where my cursor is, up till here, you would notice that things are in caps. And then it's the lowercase that begins for the rest of the description of the API, right? And inside the parentheses, you pass the arguments that are required for that API. And in general, for Fortran, you could use all caps or all lowercase. And note that in Fortran, these are like subroutine calls. So, and you have this I_error, which is an integer. You have this I_error object as the last argument to MPI calls. So majority of the MPI function calls that I will talk about today, for majority of them, the only difference between C and Fortran counterparts is that the Fortran counterpart will have an extra argument in the end, which is I_error. But for like few function calls, which I'll talk about soon, like MPI wtime, that doesn't need this I_error thing. So that's about like the syntax and how what MPI init call looks like. And then there is MPI finalize. So MPI finalize, as I was telling you, is a routine to terminate the MPI environment, and every MPI program should have one. And this is how they look like in C and Fortran. So in C, you could correlate this to the notation I told you about, MPI_f all in caps and rest of the stuff in lowercase, right? And MPI finalize in Fortran world has I_error inside it as an argument. Okay, that was about the basics. This is what every MPI program should have. Now, I will skip this at the moment, and let me just quickly go to environment management routines further. I'll come back to the slide that I just skipped. So these MPI init calls and MPI finalize calls, they come under the category of environment management routines for MPI. So besides MPI init and finalize, we also have other bunch of other routines, and two of them which we would be looking at today are MPI ComSize and ComRank. So two questions that arise early on when you're writing an MPI program is, how many MPI processes are going to be participating in this computation? And what is the rank, or what is the identification number of each process that you have in your MPI world, right? So there are two function calls that you could use to find these out. One is MPI ComSize. ComSize determines the number of processes in a communicator. Remember, I was telling you early on that MPI gives you a default communicator, MPI ComWorld, and that is used as a that you can think of as a sum total of the group of MPI processes along with the context in which they're working. So that's what MPI, that's what like com or communicator here refers to. So wherever I have communicator or com, for this session, assume it's MPI ComWorld that I'm referring to, and that's what we can substitute in the API calls here, right? So size, like as I was telling you, that is the number of MPI processes that are participating in the MPI communication or doing the computation. So if you look at the C syntax of this API call, it takes two arguments, com and ampersand size. And as I was telling you, com is nothing but MPI ComWorld. That's what you would be using here. And that's a communicator that gives the notion of the group and context to the MPI processes. And you need ampersand size. Now, okay, C programmers, do you recognize this ampersand guy? Why do we use ampersand at all in function calls like this? That is because we are wanting to pass address. This is the address of operator, right? So what we are saying here is pass the address of size. So that's what the function expects. So size is nothing but a variable of type integer that I would define in my program. So int size, for example, is what I define, and I pass the address of size to this function. Now, after calling this function, this variable size will contain the information about how many MPI processes are there which are participating in this MPI computation, right? Okay, Fortran folks. So besides com and size, you would need one more argument, that is IError. Like I was telling you earlier, you would notice yourself too that majority of the MPI calls for C and Fortran, they just have this difference, like the IError object in the end, okay? Okay, that was about finding how many MPI processes exist that I could use in my computation. If I need to determine the number of processes or the identification number of the processes within a communicator, within the group or the context that I'm working in, I would want to use something like MPI ComRank. Now, the identification number of processes varies from 0 to n-1, and the syntax for invoking the rank is like this, like MPI ComRank, and it takes two arguments, com, which is the default communicator, MPI ComWorld here, and rank is an integer variable whose address I pass here, okay? For Fortran, it's the same, two arguments plus the IError argument is the last one, right? Okay, now here comes the function, MPI WTime. Now this is the timer routine that returns elapsed wall clock time in seconds. And notice that for once, the C and Fortran versions have the same number of arguments, which is nothing, right? There is no IError object that's required for this one. So, and note that the way you write the routine, I mean the function call in C, and the way you invoke the subroutine in Fortran. So Fortran guys, you would know that when you're calling subroutine, you have to have like call and name of the subroutine, right? And C folks, you can just invoke this directly. Like you can invoke the MPI routines directly, or you can have an integer declared, and you return the value of the routine there. Okay. So as I was telling you earlier, these are some notes for the Fortran programmers. Except MPI wtime and the wtick function calls. I'm not talking about wtick today. So except these two, all MPI routines in Fortran have an additional argument, iError, at the end of the argument list. Okay? And iError is an integer that has the same meaning as a return value of the routine in C. So in Fortran, as I was telling you, MPI routines are subroutines and are invoked with the call statement. So if you are from the Fortran world, you might want to skip to slide number 67 to follow the Fortran example, the Fortran version of the same programs that we would be doing in C. So due to lack of time, I would not be explaining C and Fortran examples side by side. They are very simple, but I have enumerated all those examples that I would do in C in Fortran. And as I was telling you, you would notice yourself that pretty much majority of the things are same except for the iError argument in the MPI function calls, right? So how many people here are Fortran folks? 2? Okay, you might want to skip to slide number 67. Do you have access to slides? Wonderful. So all MPI objects are of type integer in Fortran. This is another thing that you might want to remember. So now let's do this Hello World program, and Fortran, which is in C, and Fortran folks, you might want to go to slide number 67 again. So this tiny program in C, all it does is prints the message wonderful class on the screen. And if I have to compile this, I would just say ICC-O example1, example1.c, where example1.c is the name of the program file, and the name of the executable or the output file is example1. So that's how I compile using the Intel compiler, Intel C compiler. And in order to run the executable, I just do /example1. Okay. This is how you would write a very simple C program, how you would compile it, and how you would execute it. Now we would contrast it with the process of turning this into MPI program. So if you have a very basic MPI program, how you would write it, how you would compile it, and how you would run it. So, here. Okay. So in order to convert this basic program, before I even go to the solution and start telling you anything about it, let me stop here and quiz you, just to make sure that we are all awake. So what are the 3 things that every MPI program has? Hash include, right? What else? Perfect. And termination. Yes, thank you. So we have to have hash include for MPI.h. We need to have the MPI initialization environment, and we ought to have an MPI finalize environment. Thank you so much. So that's the basic knowledge that we have gained so far, and that's what we are going to apply here on this program. So first, we extend the preprocessor directive section. We just include another preprocessor directive for including MPI.h header file, right? Then in the C program, we just go ahead and insert the MPI call for initializing the MPI environment and for terminating the MPI environment. Oh, so this is how I would start up my MPI environment. Now I'm using the signature of main that does not have the functionality to take in command line arguments. So I have nothing in the parenthesis inside main, right? So I just don't need to change the signature of main in order to pass argc-argv. I can just use MPI init and pass null values to it. So again, if you worked with the ancient version of MPI, like MPI-1, wherein this thing was prohibited, just be mindful that this is all allowed now. MPI init takes null, okay? And this is how you would start up the MPI environment. And then you do have a printf statement like you had in the serial version. And our goal is to have this message printf printed maybe as many number of times as we have the MPI processes. That's the goal of the program. So further on, what we need is the routine to shut down the MPI environment. So we insert the call to MPI finalize here, right? And voila, you got a parallel program, which now we can compile and run on Stampede. Now I'll show you how to compile and run this on Stampede in a bit, but let me quickly reiterate a few of the basic things that I mentioned a couple of minutes ago. So as I was telling you, in MPI 1.1 standard, an implementation is allowed to require that the arguments argc and argv are passed to main, that are passed to the main are also passed to MPI init. However, as I was telling you, ever since they came up with MPI 2 standard, this requirement was done away and a new MPI init routine was suggested, which takes null values instead of argc and argv. Okay. So now let's quickly go to compiling and running that tiny weeny program that we just wrote. So note that default MPI implementation that is available on Stampede is MVAPIC 2, and Intel MPI is also available. So should you want to compile this program with the Intel MPI stack, then you just need to swap the modules to load IMPI, which is Intel MPI for short. Okay, and note that by default we have the Intel compiler available also for you. Should you need for whatever reason to switch to GCC, you would just need to do a module swap. In order to learn more about these module commands, I highly encourage you to go through the Stampede user guide and learn more about how to switch from one module to another if you have to use a different MPI stack or a different compiler than what's available by default in your environment. And also remember that if you have an MPI program that you built on some other computer, now when you are porting it to Stampede, you might want to recompile the program, rebuild it, and then run it. Okay? And the command to compile a C program with MPI functionality is MPI CC. Okay? So you would use MPI CC -o, the name of the executable, which is MPI example1 here. And then you would provide the C program file name, which is MPI example1.c here. So that's how you compile the MPI program. Now notice that it's not very different from compiling the basic C program that I showed you 3 slides above, right? All it was doing is ICC -o example1, example1.c, and this guy is just doing MPI CC instead of ICC. So transitioning, the basic transitioning from the sequential programming world to parallel programming world is not that hard, as you are noticing here, right? And also remember that if you're having a C++ program to compile, then you might want to use MPI CXX. If you're compiling a Fortran program, you might want to use MPI F90 command. Okay, so all of this is again further described inside the Stampede user guide, and I highly encourage you to go and review that should you need to learn further about these options. So now we have what? We have a very basic MPI program. We know how to compile it. Now let's see how to run it. Now, whatever I'm going to show you today is specific to Stampede and TAC machines. There's a different way we run programs on TAC computers, TAC supercomputers, right? So if you have a location on some other resource, or if you want to run your program locally, you might have to find the right script or the right command to use to run your program, okay? And now I'm going to show you one way to run the program on Stampede, which is via batch submission mode. As you might have already learned yesterday, there are 2 ways to run programs on Stampede. One is in the batch mode, and one is in the interactive mode. So batch mode is via writing a job script that I'm going to show you now, and interactive mode is by invoking a session with IDEV. When you run IDEV command on the login node, that will give you access to a compute node over which you can run your MPI programs. You can do some small testing and development work there, right? Okay, now let's look at what a job script looks like, and be forewarned that different machines might have different schedulers, and you might want to work with, you might be working with different job scripts. So here we have Slurm available on Stampede. So the script I'm going to show you is using is for like writing a job for Slurm job submission system. So whenever I say MPI processes or tasks, they are interchangeable. So I do not mean OpenMP tasks when I say tasks here, okay? So with all those disclaimers, here's the script for you. So if you look at the script, what we have is pound exclamation bin bash. Your script might want to have that at the top. And then you might want to have some basic things, like you might want to choose how many number of cores are required for your MPI program, okay? The cores is specified with minus small n, this guy that's in red color. If you really don't, by default, like if you're requesting 32 cores, then what will happen is 2 nodes will be selected. So each node on Stampede has 16 cores on the host. I'm not talking about Mike at all. Just on the host, you have 16 cores. So when you run the program with minus n32, basically you need 32 cores, and each node, you know, has 16 cores. So you end up using 2 nodes here. However, if you want to distribute your MPI tasks such that you want to run, let's say, just 1 MPI process per node, then you might as well do that by just using minus capital N, just like we have minus small n here. You can use S bash minus capital N and 32. So you would provide the number of nodes to use. Now, then besides the number of cores to use, the number of nodes to use, you need to specify the queue in which you want to run the program. Now that's specified with minus P flag or minus P option. So here in this program, I have the queue set as normal, right? But if you are writing a small program, testing it, you might want to go to the development queue, right? And then note that we are required to provide the time or the anticipated amount of time that's required for your program to run. Now here, this is a gross overestimate. I have said that, oh, I want to have resources for an hour and 30 minutes. But the tiny program that we just wrote takes less than a minute to run, right? But I just wanted to demonstrate like how you would specify hour, minutes, and second, all those things like here in the bash script. So basically what you have here is minus T for specifying the amount of time required for the amount of time you would want to reserve the resources for running your job, okay? Then other basic thing that you want to provide in case you have multiple allocations associated with your account is the minus A, minus capital A flag here. So SPatch minus A followed by the account name that you want to use. I'm sorry, the project allocation name that you want to use, okay? So these are the basic things that every bash script for Slurm needs on Stampede. And then you also need to specify the name of the output file in which all the messages from the MPI environment should be stored. So when you just use minus O, in that case, only the output, when you use just minus O, then both the output and the error messages are stored in the same file. But if you also use a minus E flag in the script, that will separate the output messages from the MPI program run and the other things that you would see from standard output buffer. They go in a separate file. And if any error messages are generated, they would go in a separate file. Then you would want to have a job name, like on the top, like minus J, and my MPI, that's my job name. Okay. Having said that, having explained to you the basic components of this job script that we are going to run now, we have something called as set minus X here in the script. That's just for me to know, for example, I mean, not just for me, I mean, that's for you to know what commands are you running. So that will echo so using set minus X will echo the commands that you have in the script in your output file. So I have here something that you might find interesting, IB run, if you're already used to running MPI programs on non-TAC resources, or even non-SDSC resources, you might find, oh, that's IB run. What's that about? Now, this IB run is a wrapper for MPI run and MPI exec that was developed at TAC by my colleague who's sitting in the last row, John Castor. He developed this IB run wrapper script that basically invokes MPI run and MPI exec or MPI exec Hydra, whatever it might be, underneath the hoods. So you don't need, all you need is to know is when you are running MPI program on Stampede, majority of the times, unless there is some special reason, just use IB run, right? And IB run is followed by the name of the executable in this job script. Now, if you have a program that accepts arguments, then you would provide those arguments after the name of this executable. Okay. I'm not touching upon the various other arguments that IB run might take that I will leave as an exercise for you, and you can explore that by going through the Stampede user guide. But this is all that we need to run that tiny weeny MPI program that I showed you earlier. So that program is available already for you in the training directory, which I will show you when we go to the lab section. But if you just want to copy that code, put it in a file, compile it and run it, you should be able to do quickly even now while I'm talking about how to run the code. So basically, when I run the script, assuming this is my name of the executable that I formed after compiling this program we were talking about, let me show you the program again. So this is the program, myexample1.c, okay? I compiled it, how? By using MPICC, and I provided -o MPI example1 as the name of the executable, right? So I know the executable name. And then I go to this IB run, then I write my job script, and I provide the name of the executable after IB run. Okay. I'm all set to submit this job script now to the queue. In order to do so, I would want to use a command, sbatch. Sbatch, name of the job script, submits the job to the queue. Okay. So when the job has its turn, as in when it's running on the compute, it's done with the computation, you will get an output file produced. It would be named as mympi.o, followed by the name of the, so I'm sorry, the program keeps, the slides keep running ahead of me. So basically you have, like here I have mympi.o followed by the job ID. So mympi.o was what I specified in the job script, remember? Like here, I told this job script that when you produce an output file, please use the name mympi.o %j, where j was for the job ID. So that's what I got because that's what I specified. So I get mympi.o and the job ID associated with the job that I submitted to the queue. Okay. So look at the output. So here I have no reason why it's looking so beautiful, but you might not see the same situation when you run the program at your end. You might see that the messages from MPI processes might be overwritten, like one process might be writing and the other process might come to write something. So they might be mixed, interleaved or something like that. And there might be a good chance when you get everything streamlined like you're seeing here, okay? So just by chance that I ended up seeing something like this. So do not be baffled. So there are ways to control how to output the message to the output file that we are not going to cover in this session. I'm just showing you in this session how to run a basic C program, okay? So when you run the program and you see the output file, you would see a bunch of other messages in the output file. You will see the job ID, and you would see some messages from the environment which says setting up parallel environment for MVAPICH. That tells that I ran this program with MVAPICH 2. And then a bunch of other messages from the program. And then you would see something like shutting down parallel environment, clearing up after job. Now this is something that you did not write in the program, but that's coming from the execution of the program on Slurm, right? This is just, I'm just mentioning this so that you don't get confused when you run the labs and you see, oh, I did not intend to see this in the output file, but this will be there. So Just the red part that you have in the in this slide is what is coming from the program. Okay. At this point, before I go on explaining further MPI programs and how to use MPI, let me take a minute and ask if you have any questions in the room here. Okay, seems like everybody is happy, no questions. Let's just keep moving forward. So that was a very silly program that I showed you, wherein all we had was the include file, mpi.h, right? And all we had was a way to initialize the MPI environment and to terminate the MPI environment. And even though silly, that was a very valid MPI program, right? But it wasn't doing much except printing the message, hello world or wonderful class to the screen. Now, if I want to do something less silly than that, let's say I want to print the message, hello MPI world from process. And I want to print the process number. So I want all the MPI processes that are participating in running the program to print their ID. So that's my goal. So as I was telling you early on that these MPI processes run in a group and in a context, and you get a handle to that using the communicator object, right? And I told you that by default, we have MPI com world as the communicator, and that's what we will be using here. So with all that background information, let's look what's going on in here. First and foremost, notice that at line number 3, the main function here has a different function than our previous main function that we saw on the slide, right? This guy takes the command line arguments and it has argc and argv, okay? I still have the liberty to use MPI init with null arguments, but here in this example, because I just wanted to demonstrate how to pass the argc and argv from the command line argument or from the command line environment to the MPI initialization environment, just for the demonstration purposes, I'm just showing you here how to use this MPI init signature, which accepts 2 arguments, argc and argv. And notice how I am passing it for the C programmers with ampersand, right? Okay. So before I explain any further, let me backtrack. Let me go line by line. So, So on line number 1, we have hash include stdio.h, which does not require any explanation. Line number 2 is also self-explanatory by now. Every MPI program needs mpi.h, and that's what we have here. And then this is just the signature of main at line number 3. And then we have 2 integer variables declared, rank and size. So I'm going to use rank and size to get the value of 2 things. I want to find out how many MPI processes are participating in the MPI world, or how many are participating in the computation, and that I get by using MPI com size. And I want to get the information about the identification number of each MPI process inside the communicator. And I would use MPI com rank function call for that purposes, okay? And note that I cannot use any MPI API before calling MPI init. Therefore, before I use com rank and com size, I have to initialize the MPI environment like I'm doing at line number 5. So I set the MPI initialization environment, and after that I call this function MPI com rank, and it takes 2 arguments like we have already seen in its syntax description a few slides ago. It takes 2 arguments, the information about the communicator and the information about the integer variable in which we want to store the value of the rank. Likewise, for the size also, it takes 2 arguments, the communicator and the variable in which we want to store the number of processes participating in the computation. Okay. Now, if you look at the printf message, I had to shorten it to fit on the slide. My intention was to print both the size and the rank. That's why I invoked both rank and size, the functions to get both the rank and size here. But because I just could not fit it well enough on the slide, I just removed the functionality of printing size. But should you want to do it, all you have to do is extend this printf and put another %t in front of it and pass size as one more argument to the printf function, right? That's what. So if you're familiar with C, you know how to print. You would know how to print the value of an integer. Basically, that's how you would print size. So here, I'm just printing hello MPI world from process. I'm printing the rank %t. So %t gets substituted with the rank of the process. So this, I'm just showing how to use the rank that you found using MPI comRank function call. And oops, I'm just sorry for all of this that is going on. So then at line number 9, I have MPI finalize and then return 0. Basically, is there anything that I need to explain further in this program? No? Okay, good. Let me just go forward then. So again, how would I compile this program? Just like I showed you the compilation of the previous program, MPICC, name of the output file and name of the program file, right? So Fortran people, you would want to use MPI F90, right? So I hope you are following slide number 67 and beyond. So after I compile and run this program using the batch script, I will get this output like you see on the screen. And each process prints the message, hello, MPI world, and prints its ID, right? So I ran this program using 8 MPI tasks or 8 MPI processes. So I get this message, hello MPI world, printed 8 times, and each process prints its rank. And you see that the rank goes from 0 to 7. And that is because I was telling you, if we have n number of MPI tasks, their IDs or ranks will vary from 0 to n-1, right? So I hope this is understandable. If not, just let me know. Okay. After telling you how to write like basic MPI programs, how to compile them and how to run them, let's talk more about communication. So as I told you early on, the whole purpose of message passing or MPI here is for giving the facility to processes to communicate with each other should they need that functionality. So if there are 2 processes, for example, that are doing the computation, so basically they are running the same copy of the program, same sets of instruction, but all that varies is the data set that they're working on. And let's say after they're done with their job, what's going on is they need to combine their results. So in order to coalesce the results, they would need to talk to each other before the results are combined meaningfully, right? So that's one example of where you would need MPI communication. And in MPI world, basically, you could have a bunch of different forms of communication, but at a very broad level, you can think of these as you have point-to-point communication and you have collective communication. And each of these has further subcategories underneath them. So when I say point-to-point communication, it's just like 2 people talking to each other, one-on-one conversation. So it involves message passing between 2 different MPI processes, wherein one process takes the role of a sender and the other process takes the role of a receiver, right? And here, when you have to communicate, when you have to send the message across, you have to know that there has to be a well-agreed protocol of communication between the 2 MPI processes, okay? So the receiving guy expects to see things like, oh, what is it that I'm receiving? I want to know the data type. I want to know how much data am I going to receive. I also want to know if there is a particular tag that I need to be screening to stay on alert of what is it that I'm going to receive. Okay, so things like those make up the part of the protocol so that the receivers and senders know what they're sending and what they're receiving. Okay, and I'll show you the syntax of how to describe that in a bit. So Note that in point-to-point communication, for every sender, there has to be a matching receiver. Okay, so if you have the MPI call for sending the message in your program, but you forgot to put the call for the receiver part, you would end up writing a program that would deadlock, right? We will talk more about deadlocks and how to avoid them soon, but this is just to give you a heads up. So this diagram is just to explain you, or just to give you a visual description of how the sender and receivers could be acting in this MPI world. So assume that you have one MPI task running on a core of a node and another MPI task running on a core of another node, and and one process needs to send the data to another one. Okay. So here, basically, there are, as I was telling you, there are a bunch of ways you could do that. And with point-to-point communication, again, there are further subcategories. There could be a blocking send and receive that could be going on in here. There could be a non-blocking send and receive that could be going on in here. And there could be a combined mode of communication. Besides these, there could be other modes of communication depending upon your needs that you could use, like buffered, ready, synchronous. And I'm just not going to overwhelm you with all those details. This is just for your information purposes. And also be forewarned that the process of developing an MPI application is slightly ad hoc in the sense that you might not know what function call might work best for your program. So there might be some hit and trial required. So if you write a program that doesn't give you good performance, you might want to look at alternatives. Oh, maybe I want to overlap communication and computation, so I want to use non-blocking mode of communication, right? So things like those you need to figure out by hit and trial. So there is no straightforward recipe that I can give or anybody can give that helps you write a highly performance-oriented MPI program, right? So now coming back to these three modes of communication that I will talk about under point-to-point communication category. So for blocking sends and receives, there is implicit synchronization that's built in the call. So the sender is going to wait for the receiver to complete reading the stuff that it sent before it uses its buffer to load something else. Okay, that's blocking. In the non-blocking mode, it's so much like sending a surface mail to somebody. You write your message, put it in an envelope, put the address, and put it in the letterbox, and voila, you're done. And now it's up to the post office to deliver the letter to the right person. Okay, similar thing happens in the non-blocking mode. Basically, you just ship your message across and you get busy doing other things. But in order to write accurate programs, you have to be mindful about few things while using non-blocking mode of communication. Now, non-blocking mode of communication gives you the advantage of overlapping computation and communication, but in order to get right results, you have to keep polling the other person whether they received the letter or not. Now imagine, like coming back to the post office example I was giving you, if it's just a greeting card that you send to a friend, maybe you might not bother about it. Oh, maybe that person received it. But what if you send a check to somebody who's waiting on for your payment? You want to call them up and check, hey, by the way, I mailed a check. Did you receive that check? Something similar goes on in here, wherein you can poll on some objects which are called as request objects to check over the status, to check about the status of your message, whether it was accurately received, whether everything went well with it. So that's about non-blocking mode of communication. Then there is combined mode of communication, where you can combine the API or the function call for send and the function call for receive together in a send-receive call. And we will see example of that shortly. Okay, coming back to blocking and non-blocking mode. Before I even got to this slide, I ended up explaining you what it means. So probably there's no purpose of reading through this, but I hope you got the gist of blocking and non-blocking communication. But if you did not, or if there's a question, please feel free to ask me, okay? So that was about blocking and non-blocking. Now let's look at the blocking sends and receives. how would you describe them in your how would you write them in your program? So if you want to write the MPI send function call, you pretty much need these many arguments, 6 arguments to pass to this MPI send function call in the C world. Fortran guys, again, you have to remember to send an extra value IError to the subroutine call, right? So in the Fortran world, all that varies or all that's extra in this argument list is the last thing that you pass, which is IError, right? Okay, now let me explain the components or the arguments of this function call. So the first thing is buffer. So you need to pass the address or the initial address of the send buffer. Now send buffer could be a variable or a multivariable. Now multivariable is like an array, right? So if you are passing one value or one variable, your data count is 1. You're just passing one value. But imagine if you're sending across an array of length 10, your count would be 10. You're sending 10 values, okay? So that's what the second argument is used to specify. It specifies the amount of the basic data types or the values that you're passing. Then you need to tell what's the data type that you're using. And the data type can be the primitive or the predefined data type or the derived data type. So let me take a minute here to introduce or boast few more functionality or features of MPI. So MPI gives you the privilege to have your own, you can use MPI to have your own derived data types. So I can define my own data structures, and MPI gives you the way to, let's say, define it and make sure that it's understandable. So they give you a set of routines to do this, to write like derived data types. And unfortunately, we don't have time to cover those, but know that when I mean data type here, it could be primitive types like char, long, short. So the MPI data type for char, for example, would be MPI char all in caps. For MPI int, for example, would be MPI underscore int. If it's the long value that you're using, the data type that you would want to specify here as the third argument is MPI underscore long and so forth, okay? So those are the first three arguments of the send call. Then when you're doing point-to-point communication, you have to be precise in telling which process is it that's going to receive your data. So you need to specify the destination ID. I mean the ID of the destination process here, okay? And this process could be receiving messages from different processes, or it could be receiving multiple messages from let's say if you are a process, it could be receiving multiple messages from you. So how does it know? How does it distinguish how to screen the messages and what to do with those messages? So there's a notion of tag. So if the MPI process that's receiving, it does not care about what it has to do depending upon the tag value, then it's like MPI any tag that you would see there. But for the sender, you could have, let's say, an integer, 1. Your tag could be 1 or 2 or anything that you want to define, right? And the last argument here is MPI QAM type, as you would see. And as I told you, MPI QAM world is the default communicator that we would be using in today's session. So pretty much wherever I have MPI underscore QAM object or like value to be passed, you can conveniently assume it's going to be MPI QAM world here. Okay, that was about the sender side. Now, how does the receiver work with the data that you send? It has to intercept that data, right? So in order to be able to get hold of the data that you send, it will invoke the MPI receive call, and that takes some arguments as just like the MPI send side, but there's an extra argument here, the MPI status one. So the other arguments like buffer, I'm sorry. The buffer, count, data type, source, tag, and communicator. I hope those are clear, right? The status one, MPI status, is new here. The last argument to MPI receive that you're seeing for the C side. So let me quickly tell you what this is about. So now MPI status, or the last argument here, returns information on the message received, and it indicates the source of the message and the tag of the message. Okay. So you could poll this object to get more information as a sender. Oh, maybe yeah, I'm in the right slide. Okay. So this is just the code snippet of a bigger program. So this is not a complete program by itself. All I'm trying to show here is if you have two processes to work with, and one of them has rank 0 and the other one has rank 1, and let's say both of them are sending messages to each other, all I'm trying to stress upon here is, like, how would you order the send and receive calls in the sender side and the receiver side? Note, both of them are engaged in sending messages to each other again, right? So assume here that for process with rank 0, the destination process is having the rank of 1, and that's the only process it's going to be ever receiving the message from. So that's the source we define. So this means that process with rank 0 is going to send messages to rank 1, and it is going to receive messages from process with rank 1, right? Then we have send and receive calls inside this if statement. So I have MPI send call first. So process with rank 0 takes the role of being a sender first, okay? And it's going to send the message that's stored in out message. Now, out message could be a variable, or it could be an array having just one element there. That's why I have the count as 1 here, okay? And then I know that it's of type character. So therefore, the type here is MPI underscore char. And I know that this guy, the process with rank 0, is going to just talk to process with rank 1. So that's what I pass here as the next argument with dest. Dest is defined as 1, right? Then I define the tag that I use here. Now, tag could be defined as 1 at some place above in the program that is not shown on the slide. Then I have the default communicator, which is MPI convert. Okay, that's the sender side. Now, when this process takes the role of the receiver, it needs to read the message in a buffer or in a variable, right? That's why we have this different variable name here. It's called in message. And it again, like the out message one, it's again of length 1. It's of type character. And it's we have to define the source, as in from which rank am I going to receive stuff. That's 1 here. Then we define the tag, and we specify the communicator, which is MPI convert. And that's the MPI status object, the last one, the status thing that we pass here. That could be used for polling. And we're not talking more about how to use that at the moment. But just trust me that when you're specifying the MPI receive call, you would need MPI status as the last argument for the C side. Now, Fortran guys, again, what do you have to remember? You have to remember that both the send and receive calls, calls to these subroutines, should have I error in the end, right? And again, the examples, the corresponding example for this is towards the end of the slides, like slide 67 and beyond. Okay. So now that's about how the world looks like for the process with rank 0. Now let's look how it looks like for the process with rank 1. Now this guy also just communicates with one process, and that's the sender and the receiver of the messages it communicates with, and that's 0. That's why I have defined destination and source as 0 here. Now note, how is this guy behaving? This guy is going to act as a receiver first and then as a sender. And think about it, why is it so? It's because in the if part, wherever I have this process defined for rank 0, now rank 0 is going to send the message first. Now there has to be a corresponding receiver at the other end available to get that message. Once it has received that message, only then this process with rank 1 will take the role of acting as a sender. That's when it will send the message, maybe some other message, and that is going to be received by process with rank 0. Is that right? So there has to be, for every send, there has to be a receive. So where my cursor is at the moment, are you able to see that? So this MPI send has a corresponding receive here in the else part. And the send in the else part, like this send, has a corresponding receive in the if part here, up here, right? Okay. Now imagine what would happen if the ordering of send and receives is the same in the if and else part, just like I have it on this slide. So both the processes, they both want to be acting as receivers. And only when they have, once they have received the messages, only then they want to be acting as senders. So they are kind of in a tussle, right? They keep on waiting on each other to receive a message. But that isn't a wise thing to do. One of them needs to back out. One of them needs to be taking the role of a sender first. Otherwise, if you have a code like this, it will deadlock forever, right? In order to avoid situations like this, what you have to remember is to have the right order for your send and receives. Or if you don't want to take that pain, you could combine the send and receives in one call. And that's the exact purpose of this routine, MPI send receive. So send and receive stages that were separate, now they're still separate, but for the purpose of convenience, you have specified everything in one go, right? So notice that send and receive here, they use the same communicator, COM, which again assumed to be MPI COM world, but they have different tags. The sender one, which is in blue color, has a send tag, and the receiver one has the receive tag. So these tags help them distinguish between the messages that are being sent and received. Okay, so in this list, pretty much everything that's there in the list of arguments is pretty much covered in the send and receive calls individually. So I've color coded them so that it's easy to understand. So the blue ones are the send arguments, the green ones are the receive arguments, and the red one is what is common to both. So if you have two processes which are communicating, both of them will invoke the call to MPI send receive. Okay. Okay. All this was about blocking sends and receives. What if you want to do non-blocking mode of communication? I'll reiterate what I said previously about non-blocking. So why would you want to use non-blocking? You would want to use that if you want to overlap your computation with the communication. Note that the overall time that an application spends in running can be split into three things: the time it spends in computation, the time it spends in communication, and the time it spends in doing the I/O, right? So if you have to optimize your communication and computation, you could overlap them by using non-blocking sends and receives. As I was telling you, in the blocking mode, synchronization is implicit in those blocking calls. But here, synchronization can be deferred to a later stage. And while that synchronization is deferred, the processes can be engaged in doing some other computation. Okay. Now, you have similar number of arguments, not exact, but similar looking arguments for these I send and I receive calls. Okay. Now, I stands for immediate send. So that's what non-blocking is called. That's the second name for non-blocking calls, the immediate sends and the immediate receives. That's why we have MPI underscore I send for the non-blocking version of the send, and MPI underscore I receive for the non-blocking version of the receives. Okay. Notice that these sends and receives have an additional argument in the end, and that's the request object. So MPI request objects are used by non-blocking send and receive calls. And in C, this argument is a pointer to a predefined structure called MPI request. I think I do have an example that shows how to use the request object, but we will see. Um, so what it helps the programmer in is, it helps the programmer by giving a handle to the status of the messages sent, which can then be polled with MPI wait routine calls to see if the message has been successfully received at the other end or not. Okay. So, okay. So as I was telling you, the non-blocking versions of the send and receive routines, they can just ship their message and get busy in doing some other computation till a point arrives when they definitely must synchronize with each other before they proceed further with computation. Now, when the time is right for them to synchronize with each other, they can invoke a call to, they can call this function MPI wait. Now, MPI wait is a blocking routine, and it takes two arguments: the request guy that I was mentioning earlier, okay, in the previous slide, and the status object, right? Now, this MPI wait blocks until a specified non-blocking send or receive has completed. And you might also want to check what MPI wait any does and what MPI wait all does. That's an exercise for you. And you might also want to check what MPI test and MPI probe does, okay? We don't have, oh gosh, it's 10:23. I think I have just 7 more minutes. Okay, let me just quickly go to another concept that's about buffering. So if you have ever wondered, like, what happens to the messages when they are shipped from one end to the other, as in one process to another? So these processes have the notion of application buffers and the system buffers. So now application buffer is where you, what your program defines as the space, as in a place to hold address of a variable, a place to hold an address of the array. So now all the array structures and variables that you define in your program, they reside in a space, and that can be labeled as application buffer. In addition to that, MPI has system buffers. So system buffers are temporary parking places. You can imagine that for programs to park their stuff temporarily before they can pick the data, or before they are free to pick the data and process it. So that's not the exact definition, but that's just a coarse grain level overview of what system buffer is. So what you do with the application buffer is in your hand, but majority of the times it's the MPI implementation that has the control over the system buffer. Okay. So let's say you have some data that process A wants to send to process B. So when they're sending it over the network, this data doesn't directly go and get copied on the address buffer, in the application buffer on the other end. It first has to go to a system buffer and wait for its turn to be read by this process. And once that's done, pretty much, once this process is available, pretty much that's when it looks at the buffer and copies the data into its application buffer. Okay, so this just shows you how the data travels to the other end. So now let's quickly, in next few minutes, look into collective communication routines. So the ones that we saw so far, as I told you, those are point-to-point communication. Only two processes are involved. But imagine a scenario like now. It's just me talking and you all are listening majority of the time. So this is the example of collective communication. My sound bites are getting broadcasted to you, and you don't have any control beyond closing your ears if you want, but you can't shut me down, right? So all the processes are participating in the communication in a collective manner. If you look at this example here, this shows that how a process running on node 1 could be sending messages to multiple processes which are acting as receivers, right? Which are running on different cores. That's what this pretty picture does. So collective, when you're doing collective communication, you tend to do that when you have more than two processes involved. So it could be one to many, many to one, or many-to-many mode of communication. As in, all processes could be sending messages to all other processes in the MPI-COM world, or just one process could be engaged in sending messages to all other processes, or all processes would be engaged in sending the message to one process. Imagine all of you hate this MPI lecture and all of you start throwing tomatoes on me. So that's like a collective mode of communication wherein there's just one receiver, me, and you all are senders, right? So that's what collective communication gives you the facility to have one-to-many, many-to-many, and many-to-one type of communication. And note that all the processes within the communicator group have to have this collective call visible to them. You cannot have something like, if rank 0, then do the broadcast. So it doesn't work that way. So all the MPI processes that participate in this MPI-COM world or in the group, they have or associated with the communicator, they ought to have the visibility to these collective routines. Now, prior to MPI's 3 standard, all of the collective calls used to be blocking. But now we have neat things, which is totally up to you how you're able to utilize, but the feature by description is neat. There is a provision of non-blocking collective calls. Just like you have non-blocking point-to-point calls, we have non-blocking collective communication calls here, wherein the synchronization can be deferred to a later point, okay? So these collective routines can be broadly classified under routines for synchronization, routines for data movement, and the routines for collective communication, collective computation. So if you're going through the list of MPI routines, you would see something like MPI reduce and MPI all reduce. That's what we will use in the lab also today. So that comes under the category of collective communication. Things like if you have to move data from one process to a bunch of other processes, for those purposes, we have routines for data movement like scatter, gather, broadcast, etc. So let me just quickly go to barrier. Now, MPI barrier is used for creating synchronization amongst the processes in a group, right? This is just for your information. You can look up the syntax for barrier. But quickly, it just takes one argument, and that's MPI-COM world, or whatever the communicator that you're working with is. And now this picture just summarizes whatever I talked a minute ago, as in how does it look like from the world of the processes when you do a broadcast. So assume here that process 0 has an element, one value A, that it needs to send to multiple processes in one go. It could call something as MPI_bcast or MPI broadcast. If they have to scatter some data, as in if it has got an array and it needs to say send first 2 elements to process 1, next 2 elements to process 2, and so forth, it could use something like MPI scatter. And if it needs to collect the data back in a particular uniform manner, it could use MPI gather. In gather, it collects data from a bunch of different processes in even units. Now, there is a different flavor of scatter and gather that's called scatter V and gather V, where you can send different sizes of buffers from different MPI processes participating in collective communication. Then there's a notion of all gather. In all gather, you notice that all the processes receive the same copy of the data set, right? I'm sorry. Yeah, pretty much everybody is participating in the sending process, and everybody is participating in the receiving process. So for example, process P0 is sending A, process P1 is sending B, and process P2 is sending C, and process P3 is sending D. But the end of an MPI all gather call, all are going to have these elements A, B, C, D with them, right? So under different situations, you could use different MPI routines. So I'll skip over the syntax of these calls because pretty much I have in a high level way summarized what these do. But I'll just mention that. I'll just explain one so that you can understand rest of them on your own. So let's look at the MPI_bcast, broadcast for short. it accepts like 5 arguments, out of which buffer count and data type is same like we had in the sender side, in the MPI send calls, right? And communicator is also the same like we discussed earlier. By default, it's MPI convert. But this guy here, the 4th argument, it's root. So when broadcast is happening, one guy takes on the role of the root process or the sender. And that's what its rank is what is specified here in the root, okay? So scatter, gather, all gather is what I'm going to skip, and I'm going to directly go to reduce because that's what you would use in today's exercises. So as you would see here, in this example, all I'm trying to show is there are 4 processes and they have different data, different values. Process 0 has A, process P1 has B, process P2 has C, and 3 has D. Now, A, B, C, D is just symbolic. It could be some real data like 1, 2, 3, 4. Now, let's say you have to do something like add the values while they're collected at a place. So that's the scenario when you have to do something, some operation, some mathematical operation like summation, multiplication, or even if you have to do something like find the minimum value or find the maximum value. If you have to do things like those while the message is in transit, you could do like, you could invoke MPI reduce in that scenario. So here, all I'm showing symbolically is that the values, I'm sorry, A, B, C, D got combined and got stored in one location. Okay, so when you do reduce, the resulting value gets stored, goes to just one process and gets stored in its buffer. However, if you do all reduce, this value that you combined across through all the processes, its copy is stored in all the processes participating in the communication. So just quickly look at the reduce and all reduce API calls. So for the reduce side, you would need the address of the send buffer, the receive buffer, and you would need to know how much data is being going to be in the transit. You need to know the type of the data, MPI reduce operation, root, and COM. Now, root is the address or the place where this data is going to be stored. Okay, the process ID which will have this data in the coalesced form. Communicator, again, MPI convert, but this thing is interesting, MPI reduce operation. MPI has some predefined operations that you could use while having a call to MPI reduce. And those are, for example, the list is long, but I have just 4 here. If you want to perform a max operation, you would want to use MPI max. If you want to find the minimum of values that are being collected from different processes and stored on one, you could use MPI min. You could use MPI sum if you are going to add the values, or you could use MPI prod if you're going to multiply the values and then store it in a process. Okay, and compare the MPI all reduce call, because this is to MPI all reduce. This guy does not have root, and you can imagine why, right? Because every process is going to have a copy of this reduced data, so there is no point of having a particular process identification number there. So about to end. Yes, just in 1 second. So that was all about what you needed to know. And there are some examples on the slides. Unfortunately, we ran out of time to go over them, but I highly encourage you to go through these examples. This shows you what happens if you have a for loop in a program and you want to split the for loop computation across multiple processes. What are the changes in the program that are required to implement this? So that's what this program does. It shows you where to invoke the, how to invoke the MPI initialization environment and how to use the size and rank. This is one good example, or one non-silly example to use size and rank efficiently. I mean, to use the power of size and rank in order to do the computation. So go through this, and this shows you an example of how to use the reduce call. And there's another example that shows how to use the broadcast call. So go over these examples, and with that, I will conclude. And in this slide, I'm just summarizing the basic routines that using which you can write any MPI program. However, MPI provides you much more than what you need so that you get the flexibility and robustness of, you can take advantage of the robustness of those routines. So people have already optimized certain patterns of communication. And those optimized patterns of communication, for example, are available to you as collective routines. So if you have to do those tasks that are already available in those collective routines, then you might as well just use them rather than implement the same thing using sends and receives and other things, right? So these are the key routines: MPI init, comp size, comp rank, finalize, send, receive, and W time. And when you're doing the lab, you might want to refer to slide number 62. So this has a summary of routines that you would need to do the lab. And in the end, just be forewarned again that not all applications can be parallelized. And don't expect that every time you parallelize a program, it's going to be running faster than the serial version. You might just see the opposite of that. Okay. With that, I'll stop and let you take a break before we reconvene for the lab session. If there are any questions, feel free to talk to me about those. Mute. Here, I'll turn this off. We'll reconvene at 10:50. Thank you. I would say I would never this. There's so much IO. I think this happens so many ways to overwhelm the file system with the IO, just the IO file. Computation is rather efficient to flash until you should work with the developers to optimize. So I don't know if they were considering those that we have versions. But pretty much we do know that the computation part is not as efficient due to the IO part. There are two versions of the way to do the IO flash that impact the computation.
So I don't have IO very long. So I find the
Okay. So that's a physics asteroids part, which I'm not really about. So you're talking about.
So essentially,
A bit?
yes.
No.
So the proof of actually I have to more efficient
Really? How?
because the gravity
do not know what to say about the physics part of it, but I do know that it's relatively so I'm surprised. So is it, do you think it could be related to the class that you could be using to buy the program? So when you are using, when you define a security program using plus parallel IO, plus parallel IO or plus HDF5 type. And also, so what happens if you combine it with plus H2O5 type? And also, you will also.
Okay, so
You will have to check the exact status. I think it's H2O5 type. It's just really just different. But you don't have the exact watch. It seems like there's a bit of a blocking goal.
yeah, I've done some talks about it. Like this is
See this class just last week. We saw the increase in efficiency as a nursing house, which is so of course it was something that we could see with it. Again, I do not know what exactly they were implementing. They had been just doing margins. They were introducing that, by just making some changes on how to step out. We didn't do anything for it. We just said to try to strike one of the check. How long is it It's huge.
yeah. So it's something that
I highly recommend this very I'm not sure. I think this is it's not in the focus of the but I just feel that some options that you've seen this surface this is you've seen so I think we can do so let me send you the let me set up the block with that and then you can also Okay. So let me just take them out.
When you get started on the lab, do you ever know about this thing swap between the hybrid? They changed the lab and then overview. You switch those.
So first we will have the overview and then the.
We're switching that just so we're allowing people to, if they want to do the lab just free form, they can do it on their own, or it just.
So just the last two changed, right?
Yeah, just the last two changed.
Sure. Thank you.
Do we have people online? Oh.
I need to get stuff and stuff.
I'll get back to you after that. It's HTML5 type IO messenger.
Yeah, I see that as good. Okay, yeah.
Let me go ahead and set this up. So go ahead and
Welcome back, everyone. So just a quick overview about what's coming up. So we will have MPI Programming Lab now. That will be followed by lunch and a lecture on hybrid computing, We changed the schedule slightly such that we now have mic overview at 2 p.m. and after that, we will have the hybrid computing lab at 2:30, so that if you do not want to attend the lab or you want to do it on your own, you have the flexibility to do that. Okay, now we will switch to the labs for MPI. Thank you. So, C programmers, you might want to go to the lab which has clearly written for C programmers on the top. And the Fortran programmers, you might want to go to the Fortran version of the labs. So pretty much we have the same examples or similar examples coded in C and Fortran. And all you're supposed to do in the lab is to improvise upon them and implement extra functionality or do whatever the question asks you to do. So the slides that I have up here is for C programmers. And as I said, on the training material website, we have the lab material for the Fortran programmers as well. And it will instruct you where exactly to go, what exactly to do. So in this lab, you will learn how to compile and run an MPI program and how to make changes in the MPI program to implement certain routines. And we will compile and run the programs in Stampede here. So going quickly to what you need to do first. If you have not already logged on to Stampede, I encourage you to log on to Stampede, and you would want to use your login name, either the training account that you were provided or the one that you have from the portal. So depending upon the login name and password, as in depending upon how you registered from the tax side or the Exceed side, we will give you an allocation number on the upcoming site to use. But for now, once you're logged into Stampede, what you want to do first is copy the tar file from train 00 and then unzip it or untar it and then switch to the directory. So if you are on Linux or Mac, then you can use the SSH command that's shown here to log into Stampede. And if you are on Windows, you might want to bring up PuTTY or SSH Secure Shell Client to go to do the login. Okay. After you're connected to Stampede, run the command tar -xvzf ~train00/trainingmpi.tgz. The whole command is there. So what this command does is, from the location you run the command, at that location, it's going to copy a tar file named trainingmpi.tgz, and with the same command, it's going to also extract the contents of this file on the location at the location where you ran the command from. Okay, so at the end of the command, at the end of running this command, you will have a directory named trainingmpi, and you might want to switch to that directory. And once you're done with these steps, you have copied the tar file and you're inside the training MPI directory, we will proceed with exercise 0. So is everyone who's here already at the step like CD training MPI? Done? Okay. I'll use you as my benchmark in order to break progress. So if you registered to the Exceed portal, then please take a note of the allocation that you would be using to run the labs. So it's TG-TRA140011, right? And if you registered through TAC portal, then the project allocation to use is training-HPC, all in caps. When you switch to the directory training MPI, there would be a job script named myjob.sh. Open that script using the editor you like VI or Emacs. And once you have the script open, you might want to go to the line where you have the text A-XXXX, maybe 5 times X there. And in there, replace this 8-XS, all those things, with the right training account to use. Again, if you're from Exceed side, you want to replace this text with TG-TRA140011. And if you are from, if you registered through the TAC portal, the account you want to use is training-HPC. Okay. Now, I'm sorry, I said account to use. I meant to say the allocation to use. Okay. So after you are done with that, you might want to add one more line in the batch script. The reason why it's not already there is because I want to let you know that this reservation that you are going to have is valid for only today for a certain time duration. So we made this reservation for you so that your labs can run quickly, but outside of the lab, once you're done with today's training, this reservation will not be valid. But rest of the content in the job script will still work. So your account should be valid for another few days. I think our policy is up till 1 week. So you should be able to use the account, but the project allocation, but you will not be able to use this reservation line. Okay, so if you want your jobs to run faster than usual, you want to add this line, this reservation for including the reservation information in your batch script. You can just copy this and put it in the job script after the last line that you see in the job script. Okay. So if you have any questions till now, you can ask those. I'll leave this here till I circle around and see if anybody has any questions.
That's the right place, yes. For next 1 week, this account is valid. But after 1 week, you have to use your own education. No, not the user rate, the education. So you're a student. So if you're working here, then there are two things. Whether you are PI eligible or not PI. If you're not PI eligible, you need to find someone who can request an education and add you there. And once you add it to the education, you can use that education link there.
So assuming you all have edited the job script, let's move forward. And I hope you have saved the contents. So now in this exercise, you will learn to compile and run the MPI code. So Fortran folks, I'm assuming that you're walking through the Fortran slides on your own. So if you go to exercise 1, it will tell you which example to run and what's the command to compile the code. Now let me see if I can switch between this one. No, I ended up doing something very bad. I don't know how to bring this up and make it big. Maybe I can do this. I found it. Okay. So Fortran programmers, you might want to run MPI example 8.f, and this is how you compile the program MPI F90-O MPI example 8, MPI example 8.f, right? So basically, you need to modify the job script myjob.sh further so that you provide the right executable name after IB run, right? So once you have edited the job script so that you provide the right executable name, you have to submit the job to the queue using spatch command. And then you can check the status of the job in the queue using the SQ minus U, your username. If you do this, that will show you the status of the job in the queue. And once the job is finished executing, you can check the output file, mympi.o, after appending the job ID to it. Mympi.o plus job ID. That's the name of the output file. So let me now switch back to the other set of slides.
So I'm not sure we're still sharing.
Oh,
It's not on the. Yeah.
so how do I get back to the slide then? Maybe, I don't know.
Sorry.
No, I'm sorry. I'm trying to get back the slides for find.
You will be number.
Here.
7.
Okay,
Me.
okay, thank you. So, okay. So if you run into any problem while compiling the example code or running it, just let us know. Oh, it's that's correct. Oh, okay. Let me just get you the rest. J-R-I-G-E-L-O? G-R-I-G-E-L-O? Yeah, so using that dash, yes. And I was also not to make sure that this number is correct, but these are the only places to get around this number. Oh, I wish I'd asked you earlier. Okay, that's the text before. So that's what you put there after ID run instead of MPR example. So let's do that.
So the job script is the tool cat my job. So cat CAT space my job. Cool. Cat will display the contents of this file document. It will display it right here, and you don't have to open and close it. So yeah, that looks right to me. So what you want to do is change the time. Try changing it to 5 minutes. Just spread it. No, no, not yet. Go back. Go back. And make 1 as 0 first. That's it. That's it. And for the key, you can go. So, sorry. But also want to change normal to normal line. Dash line. Save. Oh, there's a dash missing. Go back to the job script. Yeah. Oh, yes. Oh, sorry. It's a typo there. So make it dot dash. One more dash there. Instead of the dash.
For online people, if you are using this reservation number, I just wanted to mention that there's a typo there. Instead of one dash, you need two dashes in front of reservation. So it should be pound s batch dash dash reservation equal to parallel dash day 2. Okay. Thank you.
Another file editing mode. So notice what does it say when, like, you're in the right place. So notice what it says here. It says login to WhatsApp, right? It tells you that you are on login mode. There's a notion of login modes and compute modes. Login modes are the places that you see or end up in after login mode is done. You're on a login mode. That's what you use to do the installation, compilation of the program. But you don't have to run it. You have to run it on a computer. So this script that you just submitted will help in running the program over computer. It will get hold of the computer and run this program. No, but yes. Yeah, it shows where exactly the program is /FPI example 4. So what you did in the script is basically from this line to this line. You basically described the specification about, okay, for this long my job should run in this queue. So each queue has some sets of nodes associated with it. It doesn't matter if it's numbered as C1012 or C20, whatever. Each node has a number. It doesn't matter here when I can script to provide the number. It will automatically run sort of a prompt should say penetration. That's the when you are running channels, you need to have a set aside penetration as in that's used for doing the computation. So your job runs for the amount of computation hours your job ran, those many hours, equivalent to those many hours, you will be charged for the dedication. So if your dedication was 10,000 SUs or service units, as in 10,000 computation hours on so many nodes, then what happens is if your job runs for 1 hour, now you have 10,000 minus 1 multiplied by 16. Why we multiply by 16? Because we charge on the basis of node. Each node has 16 floors. So if your job ran with a node in 1 hour, all the 16 floors were included in your job. Nothing else ran with that charge. So you ended up spending 16 SUs. So basically, you subtract it from the total SUs for that's why you're doing the action. If after running, if you have run for so long that you run your jobs for 10,000 computation hours, and you use it exhaust all the service units, then you have to request for dedication. Basically, that's what is the business of it. And then you have minus capital J, that is for output, that says this is my job. In the Q, you can see the name. So, minus points the name outside of the job functions. This is a file to the job. And the file is named like this. My job control. And here to specify the number of cores. So 32 cores means you will have 32 linear tasks in which you put in. And here we are in 2 nodes because by default all the 16 cores will be used. You can as well say my program is not a free. It will be all related on one node for each and every process. So you want to spread your task across multiple nodes. So you can specify that with S batch minus capital N 32. So that's all is going on here. Now when your program runs, can you submit a job? Is IP1 invokes MK1 MPX and space and run through this information automatically to the state. And here's what we run. What we run is here. So now if we go back to out from here to ns minus ntl. So you see this file, the job value file to produce. We're going to cap in this file. So that's the amount of movement. Okay, that was about the batch mode. Now coming back to this interactive workflow now, type IDEP. Enter. Say yes. So what's going on is this, just like in SPAT, there was a script submitted and you store all those messages. Likewise, when you do the IDEP command, something behind the scenes submits a job and gets stored up with a bunch of available nodes. Now you see what reads here. Instead of talking 1/10, you have 0.01, 0.01. But what tells you that's execution? No, that's what we need to complete this. So this gives you an interactive session. Now, you don't have to submit the job in the batch mode to this batch. You can run the program to say anyone I B run space /bar /API. it from here by typing exit. So you have a choice whether you want to do batch submission or submission through IQ. So that is the identification number of the API process. It could be one in the working on Flash.
Yeah.
Okay. I'll get back to you in a bit.
I'm trying to do it. Yeah.
Now let's go to exercise 2. So in this exercise, you will learn to use the MPI wall clock timer. So for this one, I'm assuming you are in the directory training MPI, and under that directory, there is a subdirectory called exercise. You might want to switch to that directory, do CD exercise. Once you type that CD exercise and your directory is switched, you would see an exercise named MPI example5.c. That's for the C programmers. Fortran programmers, you will have a different exercise. So, it's the same question, but for Fortran. So I'm avoiding to switch between the slides because last time I did that, I ended up wreaking some havoc here. So I'm just trying to stick to this set of slides. So if you go to my example5.c, if you're working on with the C labs, then what you have to do is read the comments in the file. The comments will act as instructions for modifying the code. They will tell you that you need to insert 2 calls to the MPI timer routine. You need to extend the variable declaration section, and you need to modify the print statement that's there inside the MPI example5.c program. So basically, some variables are already declared there. You need to declare additional variables such that you can save the value that's returned by the routine MPI timer. Now, MPI timer or the MPI WTime routine, like we looked over during the lecture, that is called to time certain regions of the code. If you want to find out how much time was spent executing particular lines of code in the program, you can invoke MPI WTime before the code region, and you can invoke MPI WTime after that code region and take the difference of time spent, right? It's the wall clock time that's returned, and this value is in double data type. So you want to declare 2 variables of type double in your program. You can name them as double T1 and double T2. I'm sorry, you can name them as T1 and T2 for T1 being the time where you call WTime for the first time, and T2 to store the value when you call the timer for the second time. And then in the print statement, you can say T2 minus T1. You can add that to print the time that your program spent running that region of code. So after you made the changes as instructed in the example file or in the exercise file, you want to compile the code and execute it via the job script that we used in example 1. Again, if you're compiling this code and you're changing the name of the executable, you have to remember to provide that executable name in front of IB run, right? And then you want to notice the output, the time taken that's printed from running this code. Basically, that's what this exercise is about. Water? Yes. Let's maybe do that. Under folder.
It's not here.
It should be here.
I think I already put it down.
I don't see that. So we go there on top of lab C, one right on top.
Oh.
Yeah, that one. Thank you.
Sure.
So the same set of instructions like we just went over for C, same apply here for the Fortran exercise. This again is the same thing that you're doing, that we discussed in C. You're going to learn how to use the MPI wall clock timer. So you can follow the instructions here on the slide. If you have any questions or are stuck, just let us know.
So you want to print that, right? So you can just use T2 minus T1 inside our package. this program basically have dictate two variables. One is the start mark. What it is doing is calculating how much work should each entity process. So it's a for loop that for starts from 0 and gives the same number of examples. And you have 10 processes which are running 5 instructions inside the code. So let us say that each process run for 10 iterations. There are 100 iterations to run, and each process runs 10 iterations on the So when you calculate start and stop points each process. So this formula start equal to rank multiplied by up to value by size plus 1. This formula gives the starting index and stopping index for each process. So originally it was not a parallel program, it's a single program, or or 1 to the right, or 0 to the right. Now you have to say, okay, if your process with rank is 0, go from 1 to 10. If your process with rank 2, go from 11 to 2. Right? And basically that's what is being done there, getting the index. So if the form initially said I for I equal to 0 at initialization, that will be updated. I equal to start, and start will be the start. So that's what happens. That way. And you calculate this end also like that start and end. So if you look at your 2 method, so the 2 goes from start to end. So the copy of the program is trying to different processes in parallel. And now they know, oh, my start and end is here. This process goes to my start and end. So it goes to the instructions. So originally this program, the serial number is finding the sum of n numbers in order to calculate the sum of statement 1 to 100. 1. Then added 2, then added 3, then added 4, then added 5. So that's what this is doing, sum to sum. Now it's parallel because now we have start and end. Instead of saying start is 0 and end is 100, we have start equal to 0 for process 1 and equal to 9 for process 2. If it's process 2, let's say it's started from other locations, 11 is the start point, 15 is the end. MPI process. So, okay. So you saw that your program got into 2 codes. On each of the code program had. So the context in which it was showing the integration act is like a different process. So there's an MPI process for each of the codes. It's talking about the copy of the program is running in the program. So it's the same instruction. But they need to know, okay, if each process does the whole task, if each process computes the sum of 100 numbers, then there's no point in parallelization. They want to define this calculation of 100 numbers. One process calculates 1 to 10, other process calculates 11 to 10. Yes. That's what this reduced thing does, combines the values in that. No? So let's say if you count from 1 to 5, sum of numbers 1 to 5. But I count from 6 to 10. In that case, we can divide the values. Let's take 4 numbers. 2 numbers. immediately change to normal action. That is Here we have the equals. Let's say you go to -8. You say -8. You go to -4. 16 is the difference. What we do is we find the meaning of it. Because you didn't specify anything to say that I think people just don't think so I recall one word is children. So if you have anything between 1 and 16, it's kind of so NGI is gives you the distributed learning model, which is not that it is even not this which is equivalent to the learning using the shared learning. So the underlying architecture of the shared learning shared learning so the programming model is distributed. So each input process you can learn you can use one word and from the next speed to very fast. Even if there are 16 words later, you can one word process over one. And it's not efficient because it definitely extends the first 16 then makes it 16. And there are one more factors. We used to get only the 16 MPI class. We get involved. Yeah, all 16 one on each group. So this is how the one. So this is how we say when we're in the about 16 kids. Two years like this, and smaller than 16, you get 4. I will get 4 and 16. So here we tell us, I want to stay around 16 and then cross to the class. But I have to run just one process per minute because the memory needs to calculation such that all the memory combinations will be exhausted for 3 minutes. So you spread it across multiple minutes. So instead of having like this, you have something like this, you can do 16 codes on the node. Only one for MPI task. So 16 more here. Now, if you call it both, if you have both mechanisms, the both of them, it's a question you ask, right? So you want to, let's say, run this MPI task such that each MPI task has both 16 and 15 processes, right? So what happens is, when you're 16 code, each and each movement part will learn 16 already. So it's like this: 16 API tasks or processes in total, and each of them 16 open. Then you have to say how many API processes to use. If you have to use one API process and 16 threads, then you should just use this. In your program, you say this code will be and this code is code. Then, this tells how many codes on which the program are having to. If you're learning to see what an infinite program, you need this many API tasks until processes. So each API process has 4 features. But what you also do is this. So let's say you request your job to run on 32 codes. But you want to make some amount of 90 ID for in your program. So you have to execute it. You will say, I want to run a particular one on 16 codes and execute it.
All right, for everyone that's watching online, we're going to go ahead and break for lunch, and we'll return at 12:45. Thank you.
Turn it off.
But
Oh, hello?
I think it's mine.
Oh, is your mic on?
Probably. There you go.
So do you want to use yours?
Yeah, I'm using mine. I'll do
Okay,
that.
that's fine. So I'll switch you. Here we go. Because I have user control
I'm part of this thing already.
here. Yeah, so we'll just change. I'll stop screen sharing here. And I'll just click on you. And then all you're going to do is just maximize your screen. And then I'll mute this one. There you go.
Right now, it's grabbing user GCC.
Oh, you know what?
That's the way that-
Okay, so if you can check if they can hear me.
It's got like about a minute.
Okay.
So go ahead and just start talking. I don't care.
Yeah, that happens the last time that I had to start twice. Anyway, after 5 minutes.
Yeah.
And that was a weird thing. He said, I'd say the same thing again.
I'm sure you can start
Say something. And then you have it. Okay. So, we're going to start the afternoon session. And we're going to be talking now about how to put MPI and OpenMP together now that you are all experts in MPI and OpenMP, right? So how all those things go together. So my name is Antonio Gomez. I'm part of the HPC group, and you have my email here, questions, comments, and you're more than welcome to send me an email, and I will try to answer at some point. So let's go. So this is what we're going to see today in this hybrid part. First, I will try to explain why we need hybrid, how we put together MPI and OpenMP, and what can you do with that, how you do it, and also I will also explain why Affinity is important for this kind of programming model. Okay, it's a little bit maybe too advanced for some of the users, so don't worry about it. In general, don't worry about the contents of this. You know, we know that in 2 days it's like too much information. You have all the slides there, and you can go through them again and learn all those concepts. And well, the last point will be just a single slide to talk about different options. It's quite new, or there are not many people talking about it. How instead of using MPI and OpenMP, other options that you have for implementing hybrid programming. Okay. So this is what 2 nodes, for example, in Stampede look like. Okay. And this is very important to understand why we need hybrid programming, or why we need OpenMP and MPI and all those things. We have here 2 nodes, the top one, but the bottom one. Each node has 2 sockets. Don't worry about what 2 sockets means right now. And we have 8 cores per socket, so total 16 cores per node, right? And those 2 nodes are connected with a network, in our case, InfiniBand. Okay? This is Stampede, and this is how many clusters in the world look like. There's nothing really particular about it. And it's very important to understand this, or to have this diagram in mind, because what you have done so far in this 2-day tutorial or training is you have been using OpenMP inside the node, right? That's what you did yesterday with Victor. You have 16 cores and you use this shared memory stuff. And today with Ritu, you were learning MPI. MPI is when you want this node to talk to this other node via the network, right? This is what you have been doing so far. And what we want to do with hybrid programming is to use MPI to talk over the network, but then to use OpenMP, shared memory, within the node, because it makes sense if you think about it. So these are the 2 parallel models that we have. On the left, we have OpenMP, where each thread has access to the same memory, to this shared memory, because this is all the memory that is inside the node. And on the right, we have MPI, the MPI programming model, where each individual process, MPI task, can run in one core, and it has access to its own memory. So they are completely independent processes. Okay? Those are the 2 models that right now you know of. So why hybrid programming? Well, if you think of the picture that I just showed, it seems very natural. You have MPI to talk from node to node, and you have OpenMP inside of the node. Why do you want to do this? First, to reduce memory. Since you are using shared memory within the node, you are just reusing that memory. You need to have many different copies of that data. You reduce the memory traffic somehow. Not really, and you reduce network traffic. Again, nowadays, due to all the optimizations that the MPI implementations do, when you are actually running MPI within the node, you are just kind of working with shared memory. It's transparent for you, but still OpenMP does better than MPI. Okay, but that is an advanced MPI. Don't worry about it. Something to consider when you are using pure MPI versus hybrid is that sometimes MPI is going to be faster than hybrid. This is something that especially MPI experts like to say a lot. They don't like OpenMP. We have one of those here. The reality is that when you're performing communication with the MPI, what normally happens is that all the OpenMP threads are going to be idle, waiting for the communication to happen, to take place. So of course, there is a bottleneck that you have there. Also, normally when you have OpenMP, especially when you're mixing OpenMP with MPI, you're going to have barriers, you're going to have logs, critical sections, all kind of synchronization stuff going on. And every time you have synchronization in this thread model, you have bottlenecks and the code slows down. The third point here is that with OpenMP or hybrid programming, you have cache coherency problems. And this is because of the design of the memory hierarchy in modern processors. You're going to have different levels of cache, and then you have main memory. You have actually two main memories in each node, and you have to have everything synchronized, and everything has to be coherent, and that's not easy at all. So you can have pretty big penalties for doing this thing. Okay, and it's not easy to fix. Well, yeah, it's not easy. Sometimes it can be really complicated. So when you're going to this model, this hybrid model, before you had one problem, which was I'm going to an MPI model, or I'm going to an OpenMP model. Well, now you have two problems. Now you have to get the best out of OpenMP, and you have to get the best out of MPI. Okay. So again, the programming models that we have, the pure MPI, pure OpenMP, and now we have the hybrid. And the hybrid, we have two main models. The first one, which there is no overlap of communication and computation, meaning you're going to have your threads doing something, and every time you need some communication to happen with MPI, all your threads are going to stop and wait for that communication to happen, to take place. Okay? And you have the second model where you are overlapping communication and computation. You can call MPI inside parallel regions. You don't have to synchronize threads. This gets challenging pretty quickly. Okay. For me, what always works is just piece of paper, and I try to draw how the communication is going to happen between threads in different MPI processes or different nodes, because otherwise it can get really messy. And how you split the data between those threads in completely different nodes. That's just how I do it. I mean, some people see this easily. I don't know. I'm not like that. So when you want to use this hybrid model, the main idea is here at the bottom. Instead of using MPI init, which is what Ritu just explained to you for using MPI, you will use now MPI init thread. And that's about it. Okay. Once you change that instruction, now you have access to this hybrid model. As you can see here in the MPI init thread, compared to MPI init, it has two extra parameters. The first one is require, and the second is provided. Require is a level of communication that you are requiring the MPI library to provide to you. Okay, and it's going to be either MPI thread single, thread funnel, serialized, or multiple. And this all depends on what you need. And provided is going to, this function is going to return a value in provided that is going to be either the value that you asked for, one of these 4 values, or a different one. And you have to check that, okay? Because if you ask, for example, for MPI thread multiple, it's because in this case, what I mean here, no restrictions. What I mean by that is just when you have MPI, when you want to use MPI thread multiple, one thread running one node is going to be able to send a message to one thread on a different node, okay? And that is the most difficult model that we have here. So if you have that in your program, and you try to init your MPI implementation with that value, and it returns that it's using serialized, that is the highest value that it supports, that MPI library, your application will fail. So you have to check that provided value against your required value. Okay? So the 4 different values that we have here, MPI thread single, that means that we don't have threads. So that is just like, all you're saying with that is that you have a pure MPI implementation. Okay? It's like calling MPI init, nothing else. Funnel means that you have one thread calling MPI. One thread and only one. And it will always be the one, the same thread. Okay? Serialized is that any thread can call MPI, but only one at a time. You cannot have 2 threads doing MPI calls at the same time. And finally, MPI thread multiple is that MPI calls can happen on any time from any thread, no restrictions whatsoever. But the main idea of here, and for example, I've been doing this for a while, and I always forget those 4 values. Because this is one of those things that you start writing your program, you write at the very beginning, and then you forget. Right? So, and then it's almost like a copy-paste from all your different programs. But all you have to know is just the most important difference is that instead of MPI init, now you have MPI init thread. That's it. Remembering that, then Google is going to help you. So this is an example of how your main method looks now. You're calling MPI init thread, again with the RGC and RGB parameters. And in this case, we are asking the MPI library to support MPI thread multiple, which is the most advanced mode. And then what we do is to check the value of provided, that variable, to check if this is actually MPI thread, if this MPI library is supporting MPI thread multiple. If it doesn't support it, I just abort, call MPI abort, and that's it, because my program would fail otherwise. I'm assuming that if I'm asking for multiple, it's because I really need multiple. Okay? And this is any hybrid code is going to look like this, in this case in C, but similar in Fortran. So as I said before, in hybrid there are 2 modes that you can use. You can have overlap between communication and computation, and you can have no overlap, and you can have overlap. In the case of not having overlap, you have the main thing is that there are no messages between the different threads or cores in the node, and you don't have many problems with topology, and don't worry about it. The main issue with this is that now when you're performing communication, all your threads are waiting for that communication to finish. So you're going to call MPI send, and all the threads are just there doing nothing. Okay? If it's not very well synchronized, you are just wasting potentially a lot of time. The MPI library must support at least MPI thread funnel, and I don't know of any MPI library that doesn't support this, but maybe it exists out there. I don't have experience with that. And this is what the code is going to look like. This is a possible scenario in this case. We are going to have what you learned yesterday in OpenMP. You're going to have pragma OMP parallel for a for loop. So only inside of that for loop you're going to have threads, right? Once all the threads have finished the for loop, you go again into, let's say, serial mode. And in that case, you just call send and receive, right? What is happening here is just since we are mixing MPI and OpenMP, we are potentially only running one MPI per node. So if we had 2 nodes, right now we have 2 MPI processes total, and we are just doing an MPI send from one to the other. And the threads, which also means that we are only using 2 cores total. Okay, all the other cores are doing nothing because we don't have threads. Right? And the other model is with some kind of overlap between communication and computation. Here you're going to have all the problems that you can have with OpenMP. OpenMP, I really like OpenMP. It's very easy to use. You have a parallel application in a few minutes, but you have to be careful with many things, especially race conditions. They happen really easily, and once you have them, they are not easy to. It's easy to see that you have one, but sometimes it's not easy to find. Okay, well, quite often it's not easy to find. Here we're going to have 2 models. One, if you think of the different models that we have, the different values, one is only one thread is going to call MPI. In this case, we can use OMP master to call MPI. You will probably need some locks or barriers here. I have some example here. And the other model is a model where all the threads call MPI. And that's why I say good luck with that. Okay? I'm going to also show you an example, the most trivial example of how to use that model. But out of that example that I show you, if you need some difficult pattern, it gets challenging really quickly. So this is how you do just having MPI calls inside of an OpenMP region. So what we have here is just we have pragma OMP parallel in line 2. So after that point, we have, let's say, 16 threads per MPI task in Stampede, right? If you had 2 nodes, you had 2 MPI tasks and 16 threads per task. So you had total 32 threads in 2 different nodes. Anyway, so we have here 16, and what we are doing in this case is just only master, line 5, we'll call the MPI function that we have in line 7, which might be send, receive, whatever function. I don't care. Okay? That way we make sure that only one thread, and only this particular thread, will call MPI. We need the barrier at the end to synchronize all the threads, because otherwise all the other threads will continue. Why do you need that? Imagine you are calling MPI receive. Okay? And the data that you receive, you need to use it in line 10 for whatever reason. Well, if you didn't have that barrier, one thread will be calling and receiving the data, and all the other threads would immediately go to try to process a data that you still don't have, because only one thread is doing that call, right? So you need some kind of synchronization there, so that the threads only continue the computation once the data has been received. Is that okay? So yeah, here you need to know the differences between the different calls in OpenMP, which ones have an implied barrier, which ones not. But you are experts in OpenMP now, so it's easy, right? And this is the other mode. The previous one was the funnel, which means that only one thread will perform MPI calls. And the next one is the serialized. That the serialized mode says that any thread can perform MPI calls. It's just that they cannot happen at the same time. Okay? How do we do that? Well, again, this example is very similar to the previous one. We're going to have here the Pragma OMP parallel construct or instruction. So from line 3 until 15, now we have several different threads. Let's say 16 for Stampede. And with Pragma OMP critical, what we are ensuring is that from line 6 to 10, there will only be one thread in that particular block. Okay? All the other threads will be waiting either before or will be after that. But now you know that only one thread and only one is calling MPI at any particular time. Right? Here now you don't need a barrier because that's what you actually want to avoid. But you have to be careful with what you do. Right? You are not, now you are just, what you want to do is that each thread is actually calling MPI to exchange data that only that thread is potentially using. Okay, that's the only way, that's a way to do it simple. And of course, now you're going to all kind of NUMA problems. I'm going to explain you what NUMA is in a few minutes, but now you're entering the OpenMP world with problems for OpenMP. Finally, we have the multiple, and this is the most difficult one. So what we have now is Pragma OMP parallel, so we have 16 threads, all calling potentially at the same time an MPI function, send, receive, whatever. And from the previous presentation, you know that when you, or if you remember, it was an hour and a half ago, when you are using MPI send, for example, you say the source, the destination, and a tag, right? The problem is that now you have 16 threads per MPI task. They all share, this is an example using 4, they all share the same MPI rank. Okay, all the threads in one node share the same MPI rank. So how can you communicate from node 0 to node 1 using source and destination if you have the same source and destination? You don't know which message you are sending, you are receiving, right? And the trick for that is to use the different tags for the different messages that you are using. So this is the easiest way to implement multiple. And let's think about this example here. In line 1 with MPI send, we are sending a buffer of a given size, count, of one type, whatever it is, let's say MPI integer, to a given destination. Let's say destination is I'm rank 0 and I'm sending this to rank 1. I'm using the task OMP get thread num. If you remember from yesterday, that call returns your thread number. So if I have 4 MPI tasks and 4 threads per task for MPI, right? It's going to return always a value from 0 to 4, 0 to 3 in this case, sorry. Because that's the maximum number of threads that you can have per node. So what you are doing, what you are trying to do with this call is that I'm sending a message from rank 0 to rank 1 using this particular tag. If I'm thread 0, I'm sending it with tag 0. Okay? And the receiver, rank 1, will try to receive from source, from 0, also using the thread number, meaning the thread 0 will will call this function with tag 0. So you will have thread 0 from rank 0 talking to thread 0 of rank 1. Okay? Yeah, you see it? That's how you achieve a kind of a one-to-one communication. You're not going to lose any messages. Kind of easy. Once you are able to picture this in your mind and a piece of paper, it makes complete sense. It's probably the easiest way to do this thing. Okay? Out of this, you go into all kind of a weird world of tags and defining tags as constants and all that, and it becomes a mess really quickly. For me, this is the easiest way. If you can somehow program your problem in this way. Okay? And that's how you use hybrid mode with MPI and OpenMP. Now the next problem, if you're going into a hybrid mode, is because you kind of care about performance. The problem with performance is that achieving good performance is pretty difficult. Okay, we have an expert here in the room. He knows a little bit about performance. He has a job for one reason, okay? Because performance is difficult. And these are expensive machines. They are designed to get good performance, but it's not trivial, okay? Some users don't care about it, and we want users to care a little bit more about that. So in a perfect world, all you have to do is you just run your configure, make installed. Now you have your MPI application. You call IV run with your application or MPI run. You get all the performance that you can get. Your code runs in 5 minutes instead of 2 days, and everybody's happy. The problem is that is the perfect world, and that never happens. It takes some time, takes an effort from you. You will have to check if all the requirements of your code are met. Meaning maybe you need more memory than what you actually have in the nodes here. Okay? You have to optimize the flags for your compiler. Again, if someone has done it for you in a makefile, awesome, but you normally have to adapt those flags to the particular architecture where you are running. You also have to find, again, the best flags for each particular MPI, and then different MPI implementations might give you different performance, depending on your implementation. You have to find the best number of cores for your problem. Some people decided, well, my application is runs in parallel. I'm going to use 64,000 tasks for my application, and it's going to run super fast. Maybe not. Okay, maybe you are just running at the same. It's taking as long as using 64 instead of 64,000. Okay, so you have to find the optimal number of cores for your application, and that's where all these scalability graphs that you can see in this parallel world come into play. And the final point, which is what this part of the presentation is about, is that you have to find the best pinning of different tasks to the cores. Okay? So where do you put each thing in this complex world of processors and nodes and everything? So, of course, when you have pure MPI, here on the left, if we have 16 cores in 2 nodes, and you only have MPI, as I said, you have 16 threads, 16 MPI tasks, well, you just put 1 MPI task per core, done. That's okay. In 2 nodes, that works fine. The problem is that when you go to thousands and thousands of nodes or cores, you go into problems with MPI. MPI doesn't scale that well at really large scale. That's why you want to use hybrid mode. Let's consider now, maybe you want to have 2 MPI tasks and 8 threads per task. Well, in that case, you want to put, if this is a socket, these are two sockets, you want to put each MPI rank in a different socket. And this is all about memory, how memory is managed in these nodes. And I have a note here I'm going to explain you a little bit more now. It just makes sense. Let's put it that way. And finally, you can have the full hybrid mode where you have only one MPI task per node, and you have 16 threads per task. In this case, it is Stampede. Well, you kind of want to put the MPI task in a specific location too, okay? But that is not that important. And why is all this important? Well, because we have a thing called, in computer, a thing called NUMA, non-uniform memory access. Here, it's all about how can you make things faster, you know, without having crazy energy requirements and while being able to increase the performance of the hardware that we have. So computer scientists come with all these ideas how to organize the memory. Yeah. Computer engineers, okay. Well, does that exist? Anyway. So they come with these all different levels of memory that they create just because accessing, if you think of a computer, you know that bringing data from disk is slow. Then you have main memory, the RAM, that is faster than disk. But then you have cache. Cache is really close to the core, and cache is much faster than main memory and RAM. So they play with all these kind of levels of memory to try to offer you the best possible performance, so that you don't have to wait too long from main memory or from disk. And when you go to these kind of machines that what we have here in Stampede, these are NUMA nodes. These nodes have two sockets, and each socket has its own, we can call it local memory. So you have 16 cores. They are divided in two sockets of 8. And then each 8 cores have their own local memory of 16 gigabytes. All the 16 cores in the node have access to the entire memory. It's just that they have some memory that is closer to them. Okay, and you have to think of all these things when you want to get good performance. And this is again a picture of this thing. I'm going to show you the real picture, and then from the people here, I have the node. This is a real node in Stampede. Okay, that I also have here. So I'm just talking about the top level here. So this is a node, or half of the node. That we have the mic in there, the table, for the next slide and next session. So what you see here is that here we have 8 cores, and here we have another 8 cores. Okay? The memory is here. You have 4 memory modules here, and you have 4 more here. These 8 cores, sorry, consider this memory local, these 16 gigabytes here. They can access this memory here, but this is local to them, meaning it's closer. Physically, it's also closer. You can see it, right? They can access this memory through here, okay? But what you want to do is that the data that these processors are using, these cores are using, you want the data to be here, as close as possible to them. Make sense? Okay, and then we have the disk here. It's farther away. It's not only slow, it's even farther. So yeah, we should put it outside. Okay, but this is a node. I always feel like we talk a lot about nodes, and people don't understand what a node is. This is just your computer, okay? Your laptop. In the same way that you have a laptop or a PC, or they have different shapes and colors, but this is it, okay? Anything? Any comment?
No, because one of the guys online was asking if you could use the mouse to plan.
Yes, I'm going to do it now. So now people in the room can disconnect for 30 seconds. So for the people online, hold on. You can play with it. So these are the two nodes. This is a typical node in a Stampede. You have 8 cores in this part here, and you have 8 cores here. Each 8 cores have what you consider local memory, which is you have 2 memory slots here and 2 here. So you have 16 gigabytes. And this is the local memory. And this is, for these 8 cores, this is the remote memory. You have 4 slots here. So you have access for these, from these 8 cores, you have access to this memory. But if you really want to get good performance, you want to use the memory that you have closer to you. Okay? And for the people online, I'll show you. This is the disk, the local disk, hard drive. Each node in Stampede has a disk. You have around 70 gigabytes for you. You can do with that whatever you want. It's in -tmp folder. And down here is the Xeon Phi. My colleague Doug is going to talk about Mike or the Xeon Phi in a few minutes. And what I was telling people here in the classroom is just, this is just all our 6400 nodes in Stampede look like this. And this conceptually is a regular computer, okay? This is your laptop, your PC, whatever, just a different shape. And of course, designed for performance, but that's it, okay? And now I'll go back to my slides. So this picture was that, basically. If you have more than one node, you're just going to have some kind of connection between nodes. It's going to be InfiniBand, for example, in our case. So how can you control which memory you are using? You know, if you're a core, how can you make sure that the memory that you're using is actually in your local memory, and not in your remote memory? Well, we have something called NUMA control. It's part of Linux. It's just a command that you can use to configure how these things is set. There are different ways of using it, different configurations, and you can try. I'm going to show you all the different options. You can try to play with them to see which one is offering you the best performance. Because I could show you here, for this toy example, this tiny example, this configuration, of course, is the best because you can see it, right? But the reality is that in the real world, sometimes it's difficult to figure out what configuration is going to be the best for you. So, as I said before, each process or thread is going to run in a core, and that core is going to have access to both local and remote memory. Remember that now when I'm talking about local and remote, I'm still talking about memory inside the node, okay? Not a different node. You're not going through the network to a different node. There is a default configuration that you can always change with this NUMA control command. The NUMA control command is you just call NUMA control, you give it some options that we're going to see now, and then you call the executable. And what you're saying is that this executable, run it with these options. And these are the options that you have. I don't know how much detail I should give you about this. I almost feel like giving you just the table and then you can play with it. But you can select, you can just choose to put all the tasks in one specific socket. So in the picture here that we had before, or here, you can decide to put all your tasks just here, for example. And why there? Because the network is closer, for example. Or you can decide to put them there. That's up to you. You can decide how the memory is allocated. You can decide that if you're running in socket 0, you only use memory in socket 0. If you run out of memory, even though you have memory in the other socket, your program will fail, should fail. You can do all those configurations, okay? You can say, I prefer that if you are running here, you use this memory. But if you run out of memory, start using the other one, right? Also, you can use a binding to CPUs. You can say, I want to use these CPUs in this order. And even, for example, this is, I don't like CPU number 5. I don't know. Because you don't like number 5. Well, you can skip number 5. Okay? So you can control everything. Now you're going to a level where you are actually kind of controlling the hardware. And you can do similar things just with OpenMP. OpenMP now is just like, it's probably too much for a 2-day tutorial. With OpenMP, you can control way too many things, okay? You can put threads in a specific course. You can leave course unused. You can oversubscribe particular nodes or course. You can do all kind of stuff. It all depends on your application, and what that means is that you have to know your application. What that also means now, if you think about it, is that you're going to spend quite some time understanding your application. Okay? That happens. So some general tips. Well, the general tip is that you want to have everything kind of well balanced. Okay? If all your computation, all your data is well distributed, logically, what makes more sense is to have everything well balanced between cores and sockets, and then in between nodes and everything. Okay? For memory policy, these are some tips. Usually when you're just using pure MPI, using the local one only is the best. When you're using OpenMP, then you go to interleave, which is better for shared arrays. Then it all depends on how you access the arrays. And not only that, NUMA also works based on first touch. What does that mean? The first process that actually touches some data puts or tries to put that data in the local memory. What that means is that if you only have one thread doing initialization of your data, it's going to try to put all that data into the local memory. And then you will have threads in other cores, in the other socket, using that memory. Okay? So you have to be aware of that, meaning that it's not just NUMA control, it's that inside your program, when you're using OpenMP, you will have to think of how you initialize your data. Okay? So it gets complicated. Remember, this is just for basically for performance. And when you use TAC, because we understand that this is difficult for many of our users, we provide this tool which is called TAC Affinity. What TAC Affinity does is it tries to use a NUMA, it tries to detect the best configuration for NUMA for your application based on the parameters that you are specifying in your batch script. Okay? That might be the best for you, or usually is, but might not be. You will have to play a little bit with it. It's only useful when you're using Mbapich, and I'm not going to say anything else about that. But the way to use it, you just call ivrun TAC_affinity, and then your program with your parameters or your arguments, and that's it. Okay. You can have a look at the code of TAC Affinity. It's just a bash script. So if you type which TAC Affinity, it will give you the path to that script, and you can have a look to see what we're doing. It's no secret. And you can try to learn from there. I had 10 minutes, but this is my last slide. Traditionally, what we had was just, for hybrid mode, was just MPI plus OpenMP. Okay? The reality is that now we have much more than that. You can use a weird mode that is called MPI plus MPI. So you will have MPI going from node to node, and then you have a different type of MPI. This is advanced stuff, but you have a different type of MPI within the node, okay? Which is using MPI3 RMA instructions. I'm just putting this here so that you have this name, in the corner of your mind. But it's a mode, and some people are really trying to push this against just, these people who actually love MPI and hate OpenMP. But yeah, it works. The idea with this mode is just, as I told you before, MPI doesn't scale extremely well at very large scale. It has problems. Why? Because it has some memory requirements, and you have to create connections. When you go to very large scale, imagine 100,000 MPI tasks, you will have 100,000 connections. I'm simplifying this a lot, but yeah. So there is a lot of memory that you're using, a lot of complexity that you have just to be able to use MPI. So what you're trying to do with this is just you're using the heavy MPI to communicate. Instead of 100,000, let's say you have 10 cores per node, you start 10,000 MPI, heavy MPI processes, and then for each MPI task, you create 10 lightweight MPI3 tasks. That way you're saving memory, you are speeding up, especially your initialization, and the scalability of your application will be higher. It's not easy to use. And then we also have something called PGAS, or Partition Global Address Space Languages. The idea is the same, is that you use MPI for the inter-node communication, node to node, and then inside of the node, instead of using OpenMP, you use these PGAS models, just because you don't like OpenMP and you want to make your life difficult. So you're going to use this PGAS stuff. What is PGAS? Well, PGAS are different languages and APIs that you can use. For example, you can use UPC, Unified Parallel C, or the C++. Good luck with that one. You have Shmeng. Shmeng was introduced by some vendors like Cray and SGI. We have a Cray machine right now here. But there is something out there called OpenShmeng, which is quite easy to use. Not as easy as OpenMP, but still kind of easy, where you can use this all intranode core-to-core communication easily. You have Chapel, another programming language, or you have this CoArray Fortran. But I'm not a Fortran programmer, so I know nothing about that. That is just for Fortran people. So these are just different ways of doing the same thing. Particularly, I still think that MPI and OpenMP is the easiest one. With OpenMP, you have to do this pragma OMP parallel 4. Beat that. The simplicity of that is just, there's nothing easier in this parallel computing world, okay? And that's it. I'm 5 minutes ahead of schedule, but I think that's fine. So if you have questions or anything, just let me know. If not, Doug, my colleague, will start in 5 minutes. He's actually coming there. So if there are no questions, we'll take a 5 minutes break, okay? And we'll continue after that. You have 5 minutes to start. Okay. How do I start?
Yeah, and you mentioned that came, no, I don't. Oh, yeah.
We should be live now, and we're 2 minutes from beginning the next talk. Just confused. Well, welcome back. I'm Doug James, and while this may be an introduction to the principles of parallel programming, it's impossible to have spent 2 days at TAC or with TAC without having heard Mike this, Mike that, and Xeon Phi this and Xeon Phi that. So it's only fair that we spend a little bit of time introducing you to this pretty exciting technology. This is a very, very rapid introduction. It's very high level. I think it's relatively low in intimidation factor. So here we go. Let's talk about one of the signature systems on about which we are very proud. I'm going to talk about what the mic is, how to use it, and I think it's only fair to make a couple of comments about the prognosis. If you ask 10 people where this technology is going, you'll get 12 answers. Today you're going to hear one of them. You'll at least hear mine. So what is a mic? It's typical in talks like this to include references at the end. I think this is the kind of technology where it makes sense to talk about up front, if you're serious, where you should look. And one of the first places that you should look is in this book about the Intel Xeon Phi, written by two gentlemen who are really the principal software architects for the layer that talk between the hardware and the programmer. It's a very, very good book, but it suffers from a major liability. It's in print, which means it's already out of date. It says something about the mic technology, and that is that this is very, very fast-moving stuff, and so you have to take this book with a grain of salt. It's worth taking, but that's worth keeping in mind. The second thing I will tell you is that probably the richest and most current source of information is the Intel Developer Zone. If you're doing your searches, search for whatever question or issue you want to do and look for hits on the Intel Developer Zone. We certainly, without trying to duplicate the documentation, include our own stuff. We've got a quick start guide. We've got stuff in our user guide. But I would encourage you to check out our mic-specific training. For example, I've got some links on Stampede to some recent training. It's only one of the recent training events where you can download all the slides, 4 or 5 labs. We're going to be doing some more at SC here in Austin in November. So check out the mic training. You know, we have 1-day course, 2-day course, whatever, that will give you more information than I could possibly give you in half an hour. Now, I think you've gotten a tour of the machine room and you've seen Stampede. I think Antonio showed you at least one half of a node on the Stampede system. What I want to do here is I want to rip open a node and sort of use that as a way to zoom in on this mic technology. We're going to basically take a node out and open it up and see what a mic is and see what it can do. So here we have it, and this is what Antonio showed you, at least schematically. What he said basically is if you pop open a node, you've got yourself a main processor, a host, if you will. We might call it a 16-core. It's really two 8-core sockets, but we've got this 16-core host or main processor. Goes by Sandy Bridge as a code name, E5, etc. 32 gigs of RAM, and it's the thing that you have been programming or at least seeing demonstrations of over the past couple days. We got 6,400 of these babies, and more or less they're pretty much all the same. We have a couple specialized nodes, but these things alone will give you more than 2 petaflops of performance. However, within each or at least most of the nodes, we have an assistant processor, a coprocessor that's called the Intel Xeon Phi mic. Here's a schematic. It's connected to its main or host processor using a PCI Express cable. And here, in the other side of the case, you can see a Xeon Phi coprocessor, an assistant processor, together with the PCI cable that connects it. Now, this brings up the first important point about the Xeon Phi. One of the concerns, one of the criticisms, one of the risk factors that you hear people talk about is that you have to move data between the host and the Xeon Phi coprocessor over this really, really slow PCIe bus, and that's one of the major limiting factors in using this device. There's some truth in that, but I think it's overblown. My perspective is, if you look at the bandwidth between the coprocessor and the main processor, you will see that it's roughly, in fact slightly faster than, the bandwidth between nodes, host to host, that you would encounter when thinking about MPI. So the same considerations, the same thought processes, the same questions, the same programming issues that you encounter when programming pure MPI, node to node, are the same programming issues, questions, constraints when programming between host and coprocessor. It is not an accident that the bandwidth is roughly the same. Now, what I want to do is I want to compare and contrast the host side with this assistant coprocessor called the MIC. And let's first talk terminology. MIC stands for Many Integrated Core. It's an architecture. The current product line in that architecture is Xeon Phi. Some people will say, well, MIC's been replaced. No, one's an architecture, one's a product line. And it's at least worth saying the ones we have were the first production, large-scale use of the system. And so we actually have some that you can't buy in the store. You could go to Fry's and buy a MIC right now. It would be a slightly different product line than the one that we have in Stampede. Together, the mics on Stampede add an additional 7 petaflops, 400,000 cores, to the power of Stampede. And so it's a serious hunk of additional processing power. Now let's compare and contrast. The first thing I will tell you is that there are 16 cores in the host and 61 lightweight cores in the mic. I say lightweight, let me say it again, lightweight. For the cost of a light bulb on the host, you've got 16 cores doing their thing. For the cost of that same light bulb on the mic, you've got 61 lightweight, low power cores doing their thing. Now there are people here that hate me saying this, which is why I like to say it. I think of it as 16 stallions and 61 rabbits. And the game is to figure out how to program this node so that you can make use of the stallions and get some useful work out of the rabbits. You also, the second contrast I will make, besides the lightweight cores, is that you have 32 gig of RAM on the host, shared among the 16 cores. Right now, in the current generation, you have 8 gig of RAM on the mic, shared among 61 cores. And so one of the constraints on that device is the RAM limitation. From the point of view of clock speed, basically the cores on the mic, they're lightweight by design. They're about a third of the speed of the host processors. And in fact, they're sort of lean and mean in the sense that a lot of the power-hungry capabilities have been removed. So, you know, they're designed to be stripped down, low power things, and you know, that's sort of their essential, if you will, their signature characteristic. On the other hand, to compensate for that, they have very wide vector units. Basically, they've got a vector unit that's twice as wide as the main processor, and we'll have a moment about what that means. The good news is they vectorize very, very well. The bad news is, because they're lightweight cores, you really need to vectorize to get good performance out of them. Let's remind ourselves, I think it was C that introduced you to the idea of vectorization, and you've probably seen a little bit about that over the past 2 days. Remind ourselves what this means. Essentially, it's assembly line computation. We've got these loops with tight, simple arithmetic operations, something like AX plus Y, and instead of doing 1 per clock cycle, we're doing 8 per clock cycle, and it's 8 results, each of which can be a multiply and an add. So you can, at least in theory, get 16 computations per clock cycle per core because of the very, very fat vectorization built into this device. And to make it go fast, this is something that's important to keep in mind. One of the things that sort of is sort of a signature characteristic of this device is that, unlike a graphics processing unit, a GPU, this is a device that actually can run as a standalone computer. It's running Linux. You can log into it. You can go over and look around. Because it's only got 8 gig of RAM, and because it doesn't have any spinning disk or SSD or any other storage, everything's got to be in RAM, it's stripped down, you know, so you only have the essential tools and the essential pieces of Linux. But it's a device in itself, and you can go over there and log in, and that's going to have some programming implications. On the Stampede system, all of the shared file systems, home, work, and scratch, are available and visible on the mic, but they're visible because of magic. You know, much of the magic is done by the host on behalf of the mic. I will point out that we do have almost 500 nodes that have 2 mics each, 2 mics connected to the processor. It will not take you long to realize that I am not an artist, and no matter how I draw this picture, I can't seem to draw it in a way that conveys the idea that each of the mics is connected to the host as a whole. It's not like there's a mic associated with each host socket. But no matter how I move these arrows, it just doesn't work. So just accept that as a limitation of the artist or the artist wannabe. So how do you use this thing? Well, depending upon how you count, there are at least 4 ways to use it. And what I'd like to do is talk about what that means in terms of you as either the end user of a program that already uses the mic, or as a programmer who's contemplating migrating code. How you run depends on how you use the mic. It is possible to take any of these 4 ways, actually 3 of the 4 ways, and sort of combine them in sort of a hybrid model, similar to the kind of things Antonio had to say, and we'll mention that briefly again. So, can you use it? First, one way to use the mic is to ignore it. Now, that may seem like a silly thing to say, but every once in a while you'll encounter someone that says, gee, I can't work on Stampede because it has mics, and my code can't use mics. Of course you can use Stampede, and the first step in migrating to mics is probably getting your code working on Stampede without mics. 2.2 petaflops without mics, I'm guessing that's enough for most people. And it's important to remember that this is a perfectly acceptable programming model. We have queues that are designed to support this programming model. The second method of using a mic is to use a single mic as a standalone computer. A single mic as a standalone computer. Intel calls that mode the native mode. It's essentially, it's a lie, but it's a useful lie. It's treating the mic as if it didn't even have a host. And to do that frankly, all you have to do is add one new flag to your compile line, mmic. You're using familiar programming paradigms in C, C++, or Fortran, so you have source code compatibility with ordinary, traditional, run-of-the-mill, garden variety vanilla code. And all you have to do is create a mic binary, and you do that with mmic. To run the code, after you've compiled it on the host, there is no compiler over there, you can SSH to the mic and run it over there, but you don't have to. It turns out if you just launch the thing from the host, the infrastructure, the runtime environment is smart enough to say, oh, this is a binary that needs to run on a mic, and it will move it over there and run it on the mic for you. It is certainly possible to do a lot of different things natively. OpenMP is certainly a very good model, you know, having 30 threads, 60 threads, that kind of thing. And certainly pure MPI is possible, but when you think about the limitations, the memory limitations, pure MPI is probably not a practical model for production code unless you're just trying to learn something. Because, you know, if you think about typical production code, maybe using 1 to 2 gigabytes per task, you ain't going to have a lot of tasks over on a mic. And if you don't have a lot of tasks over on a mic, you're leaving a lot of those rabbits idle. And so from a production point of view, MPI plus something else, maybe, as Antonio said, MPI plus OpenMP. Serial code, you don't want to go over there and run on one core. You get, you know, 1/3 the performance of your host, maybe less. And frankly, for the reasons I just described, pure MPI is probably implausible.
One question for you.
Yes, sir.
So if you run this code without any parallel contract, so no OpenMP, no guidance, is it still an advantage just from the access to the vector?
No, it's not likely. I mean, you remember that you're talking about, I mean, anything's possible, but remember you're talking about a processor that has 1/3 the clock speed, and a lot of the other optimization, hardware-based optimizations are taken out. You know, there's all this, you know, at a sequence, you know, there's all this stuff that makes processors do really well, and not that. No, yeah, you don't want to be running serial code over there. Okay, the bottom line, and this is going to be important moving forward into new generations of mic, is good performance on this device requires you to expose a high degree of parallelism. If you're not exposing parallelism, then you're not going to be able to make good use of this device. I mean, it's that simple. It's not magic. The second, I guess if you start with 0, the 0th mode was don't use the mic. The first mode was native. Mode number 2 is offload, where you're using mic as sort of an assistant processor in the service of the host. So essentially, the picture you should have is you've got this application running on the host, and the host basically issues an order. And the order is, dear Mike, do some work and deliver the results back to me. So this is the traditional coprocessor, the traditional assistant processor. This is the way GPU programming is done. So a program running on the host offloads to the mic. This is like GPU programming, but it's done in ordinary C, C++, and Fortran. What's really cool is you don't change the compile line at all. You just compile. The compiler and the runtime environment are smart enough to manage things. You do all the programming here using directives that look like OpenMP directives, the same kind of thing you saw. I think it was Victor who showed you those yesterday. It's done that way. In a perfect world, when the host directed the coprocessor to do some work, the host would stay active. So the host would work while the mic worked. I call this offload in addition to mic versus offload instead of mic. It would be a real shame if you directed an offload and then those 16 stallions waited until the mic were done. In an ideal world, both would be active. From a practical point of view, that's hard to do. That is hard to do, but that's you know, what you would do in an ideal world. The third model is to do MPI where some or all of the MPI tasks are sitting on a mic. So you could imagine, you know, 1,000 MPI tasks, all of them on the mic, or 1,000 MPI tasks, maybe a third of them on the mic. Intel calls this symmetric mode. To compile, what you have to do is build 2 versions of the executable, one for the host side, one for the mic side, and then there's a special MPI launcher. You've seen IB Run, we call it IB Run Sim. It sort of manages the details for you of distributing the tasks in the way that you want between host and mic. Now, there are challenges to this mode. One of them is heterogeneity. I mean, you've got devices with different capability. How do you partition your problem to, you know, honor that, if you will? You've got RAM differences, performance differences, etc. Another challenge is communications. All communications between mics have to go through their hosts. And frankly, there's challenges related to file operations. Since the mic has no disk of any kind, all file operations go through the host, and they are very, very slow at best, and they are problematic at worst. Now, I'll have some more comments about where the technology is heading, but that does make for some challenges. You don't get nothing for nothing. And there's work involved in exploiting devices like this. But there's one place where you come close to getting nothing for nothing, and that is what's called automatic offload. Automatic offload is basically offload mic usage that's built into the Intel math library, the math kernel library that's commonly called MKL. You know, you've seen other math libraries. You've seen GSL, the GNU library, perhaps. The Intel library is MKL, and built into the MKL is the ability to use the mic under certain conditions automatically with essentially no programming effort. It's for computationally intensive linear algebra. Basically, think matrix operations that are big enough to justify moving the data. And it's accomplished by calling the MKL and letting the MKL manage the details. Now, I have to tell you, I don't know where the marketing people were when they named automatic offload, because automatic offload doesn't do justice to what's happening. Automatic offload, what the MKL actually does is it decides how much work to do on the host and mic, and it distributes the work across host and mic in a near optimal way. And that's pretty dagnab amazing. This is perfect offload. It's host plus mic, and it's doggone near for free. All you have to do is set an environment variable or 2. What's really cool is a lot of applications that you and I use call MKL without us knowing about it. And so, for example, we've got automatic offload built into MATLAB, R, and Python. Because if I call a matrix multiplication in R or Python or MATLAB, it can call MKL to accomplish that computation, and therefore I can exploit automatic offload almost for free. Now, the good news is it's easy to do. The bad news is it only works for computationally intensive linear algebra of sufficient size. Again, matrix multiplication. Think thousands of rows and columns by thousands of rows and columns, but it's the doggone near easiest thing. It's so pretty, it's slick. If you're interested in seeing how to do it, you can download a lab to see how to do it on Stampede. There's also a quick start guide. It's sometimes hard to find the link to it, but it's really easy to search for it. And I'll tell you, it's pretty nice. If you go to Python and you just log in and do an 8,000 by 8,000 matrix multiplication. I know I've done this. Under default conditions, it takes 45 seconds. If you're smart enough to recognize that that's because you're not threading at all, you can get it down to 6 seconds. I have to tell you, if you use AO, if you use automatic offload, 2 seconds. That's a pretty good speed up for the cost of setting a couple of environment variables. It's a nice little thing. Now, where's this technology going? If I'm a principal investigator, if I'm a researcher, you know, one of the things I have to do when I see some newfangled technology is I have to evaluate where it's headed. You know, is this worth my investment? Is this going to, you know, if I invest 1,000 hours or 2,000 hours or 10 years of work and the technology goes away, that is not a good thing. Okay, so I have to evaluate this. And one of the things I have to evaluate is not just is the technology any good, but what's the risk, the market penetration. Let me give you my assessment, and then you can take it or leave it. I think two things are absolutely clear. One thing is clear is that there is a battle between the folks on the Intel side promoting the use of this many integrated core technology, sort of this you know, C++ standalone computer, and the graphics processor unit folks, primarily NVIDIA. So it's sort of a market battle between NVIDIA and Intel. And Intel will tell you that the mic marks the end, the death of GPUs. And NVIDIA will tell you that this is a flash in the pan, right? And I think reality is somewhere in between. So let's talk about where it is. The second thing that I think is absolutely, without question, true, is that we're going to have a trend toward more cores on the chips. I mean, that's just the only way that we can scale right now in an era where power is becoming a limiting factor. So you're going to have more cores on the chips. Whether those cores sit on a device that complies with the, you know, that is an Intel architecture is a separate question. But the things we learn from more cores on the chips in the mic are going to be useful things. So what about market penetration? I think it's fair to say that the mic is hitting its stride. I mean, you've got at least 2 machines in the top 10 that have mics. You've got a number of machines around the world that use mics. You've got a major DOE machine coming online that's going to have the next generation mic in it very, very soon. And I have to tell you, we're parsing this sentence very carefully. Mic-equipped systems now generate more flops in the top 500 than GPU systems. Now, I didn't say mics generate more flops than GPUs. I say systems that have mics are common enough and important enough and generating enough core hours that they are now dominating the top 500. I can also tell you the next generation device is very interesting. The current device exists only as a coprocessor. The next generation device, which will come out next year, is available as a standalone host. You can buy it as a standalone host. And in fact, that's how it's going to first appear. You don't need to buy it as a coprocessor. It doesn't have to hook up to a host. It's going to have, call it near memory, fast memory, on-package memory that's 5 times faster than traditional memory. And that's in addition to the traditional memory you can add to it. And this is pretty cool. It's going to have doggone near perfect binary compatibility with the current generation of Intel processors. I say near complete because there's a couple of specialized intrinsics that are not going to be available on the KML, but kind of programs that you and I write, you can compile them once and they can run either of those 2 places. This is very interesting. So this technology is going to be around at least for another generation. You're going to have to make your own bets, but I'm betting that research effort intended to expose the parallelism necessary to make devices work on many core architectures is going to be research effort well invested. There are many MicAware apps on Stampede. You know, you won't be surprised to know that we've got infrastructure and tools. You know, we've got compilers, MPI stacks, you know, various development tools. I think the, you know, production science applications are coming along more slowly, but, you know, things have to happen in a certain order. But we do have chemistry codes, climate codes, math codes, you know, that make use of the mic. We also have I/O codes. We don't encourage I/O from the mic, but if you're going to compile your codes, say in an MPI mode, we have to at least resolve the library calls, and we may have to make a few. And of course, we've already talked about automatic offload. There's a lot of folks doing stuff in their user accounts that you know, go beyond the system installs. There's some serious work going on. What everybody wants to know is, can I port my code to the mic? And the answer is, yeah, probably. Porting is generally easy. You know, I said, and I wasn't kidding, that all you have to do, in theory, is add a new flag. In practice, the devil's always in the details, and I would say that a fair assessment is that porting your code is as easy as the availability of libraries. That if you have 42 libraries you need, you're going to need 42 libraries on the mic side. And if 31 of them are available, then there's 9 you have to build. Okay? So porting is easy, modulo the existence of libraries. But that might be the wrong question. The real important question is, will Mike improve my code's performance? And that's a harder question. And the answer basically is, it depends on how much parallelism you expose. This is not a magic device. Your code doesn't just go faster because you ran it on a mic. In fact, it may go slower. But the hard work is in the optimization. What are the strengths of the device? Well, one of the strengths of the device, as I said, is this is not just a coprocessor. It's a standalone device, so you can do things other than the tight computational kernels that you would have to limit yourself to if you were doing, say, GPU programming. And I have to say, there's advantages and disadvantages to GPUs. There's advantages and disadvantages to mics. But one of the big advantages to mics is familiar programming models. C, C++, Fortran, OpenMP, and MPI. And that is a non-trivial thing. One of the subtle things about a mic is that when you optimize your code to run well on a mic, you are doing things that will also improve your host side code, because you're doing things to the C and C++ code that you're running over there anyway. It's not unusual. In fact, it's pretty doggone common. If you put the effort in on the mic side code, you'll find your host side code probably, it's not unusual to see 2 times the performance. And I think this is worth saying, because sometimes you read in the literature, yeah, the GPU code is 50 times faster than the host code, or 100 times faster. Well, I'm here to tell you, GPUs aren't 100 times faster than their hosts. What we're talking about is an optimized GPU code running against an unoptimized host code. And here's an example of where the work done on the coprocessor side is going to do you some benefits. And I have to tell you, everybody wants to know, can I write once and run out everywhere? And I like to believe, no, not in this lifetime. But people that have been programming on the GPU have already done the hard part. They have already, at a gross level, at a top level, thought about their algorithm and partitioned it into some work that can be done on another device. That's the hard part. Now, there are some issues, okay? One of the issues is the same as it is with any supplemental device. It's, can I transfer data and then do enough work to justify the movement of the data, amortizing the transfers? How can I make the mic and host work together? Because that's asynchronous programming and that's hard work. File operations from the mic, the current generation of mic, is a problem. It may not be quite the problem in the next generation when we have mics that are sort of standalone devices. Library availability continues to be an issue. I mean, you can only develop stuff as fast as the literature, the hardware, the software stack, and things happen in a certain order. And the fact that in the current generation there's only 8 gig over there serving 61 processors does become a problem. I think emerging issues, if you talk to the OpenMP folks, they'll tell you that's the next and the only and the leading and the important specification. What about OpenACC and OpenCL? Who wins the battle? I have an opinion. Everybody has an opinion, but the evolution of specifications is an emerging issue, as is the question of whether there will ever be a coprocessor in the next generation. Everybody wants to know whether Intel is going to release the KNL in a coprocessor version. I think even Intel doesn't know that, because it's a market decision. Intel's a big enough company to see how the market responds, what the demand is. What's the bottom line? Well, I think the bottom line is there's just no doubt that we're at the front end of disruptive technology. Many-core is here to stay. Whether Mike is here to stay is an open question, but Many-core is here to stay. And I'll tell you something else. If you're willing to put in 2 weeks of work, you can become the world's leading expert on some aspect of the mic. And then all you have to do is stay 2 weeks ahead of the rest of the world, and your career is made. Okay? The bad news is this is a fast-moving target. It's hard to develop against something where even the documentation can't keep up with reality. Okay? What I would advise you is that porting is easy. That's not the issue. Performance requires hard work, but that hard work is going to benefit both sides. I think you're going to like it. Don't take anything I say for granted, because I've never been known for my objectivity. I believe in this place. I believe in that device. But I hope that enthusiasm says to you, gee, maybe I want a piece of that too. Hey, thanks for putting up with me. I think Antonio's got the next piece of the day. All right. Jason, do you want me to unplug or wait for you to come up here? Okay.
So this is just the last presentation of the day, and we moved it for different reasons. First, because I think it makes more sense like this. Second, but it's going to rain a little bit here. So if you want to drive back home at some point, I think it's a good idea to do it. Feel free to do it. Something good about this lab is it's self-explanatory. You can just follow it. Okay, so you can do it now. You can do it at home. All the instructions are there. The slides are, or the examples, or the tutorial is about how to use NUMA control. So you can see how different options for NUMA control affect the performance of your code. Everything should work. You have the reservation today. So you can just follow the exercises. It should be really quick today because of that reservation. And I'm going to be here. We're going to be here helping people in the class, helping people in the room. Also, I don't know if some of you have a meeting with one of us to talk about your codes. You can decide if you want to have that meeting now. Also, Doug mentioned about the tour. You haven't had a tour. I think we can also give you a tour of the machine room if you're interested in that. We can do it now, and as I said, you can do all these exercises at home. Okay, this is not really that difficult, I have to say. Okay, so it's up to you what you want to do. You can stay here. If there is interest, we go to machine room, whatever you prefer. Okay, so just let me know, whatever, here in the room. And you can just give a tour even for just one person, it's fine, no problem at all. It's kind of chilly in there, yeah, okay, but yeah. So, you okay with that? You're not going to the machine room? Okay. So for the people online, You can post your questions there, and we'll answer them as soon as we can.